So this is going to be our next unit on the normal distribution. So the normal distribution, this is going to be your next unit, normal probability distribution, and the guided notes that go with this. So we're going to get through this. The labs are in front of you. They are due on the due dates. Your test will be, let me look and see if I get the exact day here. Day your test is Monday the 28th. So that means corrections for this test are due on that day as well. All right, so what we talked about in the last unit primarily was the discrete distributions. So now we're going to talk about a continuous random variable. Now, continuous random variable technically has an infinite number of possible values that can be represented by an interval on the number line. Hours spent studying in a day can be between 0 and 24. Now, when most people talk about like amount of time they spend studying in a day, they'll usually just say, round that up to the next hour or whatever. But that's going to be a continuous distribution. And continuous random variables, one such particular example that we're going to be heavily focused on is the normal distribution. So the normal distribution is going to be a bell curve that is in fact bell-shaped and symmetric. And here's an equation for it. Now, you don't have to memorize it. We're not going to really use it because, well, we're going to use the calculator for it. But this equation that you see here is going to have two parameters. It's going to be based on the mean, mu, and the standard deviation, sigma. So if you look at this equation, you might freak out like, oh my God, I got to work with that. No. We're going to be using tables and technology, mainly technology. I'm going to show you the tables, how they work, but we're going to be much more reliant on technology. So basically, we're going to look at a uniform distribution, which it's going to be a uniform distribution if the values are spread evenly over the range of probabilities. And it's going to be a rectangular shape. So we're going to be using a lot of what are called density curves here. These density curves are going to be the graphs of continuous probability distribution. And believe it or not, they're actually very simple to use here. The total area under the curve has to add up to 1 or 100%. And every point on the curve has to have a vertical height that is 0 or greater. In other words, the graph can simply not fall below the x-axis. It can be on the x-axis, but never below it. So, the total area under a density curve is equal to 1. And there's going to be a direct correspondence between area and probability. Now, these aren't the type of density curves that we're going to be working with mainly, but one of the things I really want to emphasize is this entire curve, even though it's more of a rectangular shape than anything, it's going to have an area of 1. And that's the key for any density curve that we're going to be working with in this course. It's going to have an area of 1. Because, for instance, if we wanted to find the probability that a randomly selected voltage level was higher than 124.5 volts, basically you take the distance, the horizontal distance, multiply it by the vertical distance, and area is length times width. You know that. Now, the entire horizontal distance is 2, and the entire vertical distance is a half. 2 times a half is what? It's going to be 1. So, now we're going to learn what a z-score is. What is a z-score? Well, the standard score, or z-score, will represent the number of standard deviations that a value falls from the mean, mu. So, for instance, this is the formula for a z-score. It's going to be x minus the mean over the standard deviation. So, in 2009, Heath Ledger won the Oscar for Best Supporting Actor at age 29 for his role in the movie The Dark Knight Rises, or The Dark Knight. Penelope Cruz won hers at age 34. Now, what is the purpose of calculating the z-scores for actors and actresses? Well, it's simple. What happens is we take into account the mean and standard deviation for each group, because there's obviously a difference between actor and actresses. So what happens is, for Heath Ledger, his z-score was negative 1.49, which means he was 1.49 standard deviations below the mean. Now, for Penelope Cruz, we use a different mean and a different standard deviation because, well, it tells you to. And her z-score is negative 0.42, which means she is still below the mean. That means it's below average, which is a good thing. Now, z-scores that are within 2 standard deviations of the mean are what we would consider ordinary. Once we are outside of 2 standard deviations from the mean, whether it be positive or negative, that means we are in the unusual territory. And that is something unlikely to occur. And if you're within 2 standard deviations, that is considered ordinary or usual. So the higher your z-score is, regardless of the sign, the more unusual something is. Now, if you're more than 2 standard deviations above or below, it's pretty unusual. If you're more than 3, that's very unusual. If you're more than 4, that's freakish. So, I want you to find the z-score for Christopher Plummer. First off, how old was Christopher Plummer? Now, I'm putting 85 as a subscript. So we would take 85 minus, and let's see what's the mean for males, 49.5. And the standard deviation for males was 13.8. So 85 minus 49.5 divided by 13.8, and I got a z-score of 81? Something is not right with that. Did I do something wrong? You got to put parentheses. And we're going to get 2.57. Now, what that means is, obviously, Christopher Plummer, his age of getting an Academy Award is much higher than normal at 85. Was it Academy? Oh, no, Oscars. Well, it's all these awards are farces anyway. So, Christopher Plummer was 2.57 standard deviations above the mean. Now what I want you to do is I want you to try this. If your heart rate is 105 beats a minute, mean is 72 with a standard deviation of 18, is it unusual? Usual and unusual. So let's see here. A heart rate of 105 would be 105 minus 72 over 18. And that would be 1.83. So is that considered an unusually high heart rate? No, this is not unusual. If you were more than 2 standard deviations above or 2 standard deviations below. Correct. The first one was unusual because that was more than 2 standard deviations away. If it's 2 standard deviations above or below. So the bounds for unusual, basically 72 plus or minus 2 times 18. 72 plus or minus 36. I don't know where they get this from. 36 to 108. So, I mean, if you had a heart rate below 36, I don't know. I don't think that's good at all. But, by this standard, by having a heart rate above 108, so basically this is the usual bounds. If we went below 36 or above 108, that is what we would call unusual. So that's what we get for that. All right. Questions about that? Okay, so now the empirical rule, this is actually mentioned in the books back in chapter 2, but I don't mention this at that point because we don't go as deep with it nearly as I would like. So, for data that has a symmetric or a bell-shaped distribution, and we're going to be basically making heavy use of the bell curve in this unit. So what's going to happen is about 68% of the data will lie within 1 standard deviation from the mean. About 95% will lie within 2 standard deviations of the mean. And lastly, about 99.7 will lie within 3 standard deviations of the mean. And what we're going to do later on is we're going to figure out what these percentages are exactly. So this 68, 95, 99, 7 rule is merely an approximation of sorts. Now, what happens is, here in a survey conducted by the National Center for Health Statistics, the sample mean height of women in the United States was 64.3 inches with a sample standard deviation of 2.62 inches. We're going to estimate the percentage of the women between 59.06 and 64.3 inches. So, what happens here is 64.3 is the mean. And what was the standard deviation listed as? 2.62. So basically, what we want to do is subtract 2.62 inches. to get our thresholds. So yeah, 64.3 minus 2.62, we would have 61.68, 59.06, and a third standard deviation below that would be 56.44. Now, let's go above that. Now, by the way, 64 inches is how tall? In terms of feet. 5 feet. 5 feet 4 inches. Now, if we wanted to go above the mean, going 2.62, one standard deviation above would be 66.92. A second standard deviation above that would be 69.54. And a third standard deviation above that would be 72.16 inches. Now, for relative purposes, 72 inches is how tall. Six feet. You don't see too many women that are 6 feet tall. My sister is 6 feet tall, but that's, I guess, how it works sometimes. So what I want you to do is to estimate the percentage of women whose heights are between 56.44 and 66.92. Now, while you're doing that, let me talk to you about the bell curve a little bit more. In addition, to the fact that we're going to be working with that, the other thing that I didn't quite mention here, how many of you are familiar with the term grading on a curve? Students have always asked me, is this class going to be on a curve? And my answer to that is always no. I do not curve. And number one, I don't curve in a small class. Curving is typically done at large state universities. But the way a lot of people perceive grading on a curve is that what typically happens is when they say the curve for this class is this, they usually are just simply rescaling the grades. Like, we're going to see in detail what grading on the curve really would mean. All right, so 56.44 to 66.92. So if we added those percentages, let's see here, 2.35 plus 13.5 plus 34 plus 34. Do I go any further? No. So let's see here, 81.5. So what does this add up to? 83.85% of women are going to have heights between 56.44 and 66.92 inches. Now, we're only doing estimations here. A little bit later on, probably tomorrow, we're going to actually learn how the curve really works. A little bit later today. We're going to find the exact values. So what is the normal distribution? The main properties are simply that the mean, median, and mode are all equal. And the graph is going to be bell-shaped and symmetric about the mean. Now, the total area under the curve is equal to 1. Now, what happens here is the normal curve approaches, but it never quite touches the x-axis. And basically, Think of it like an asymptote. Those of you that have taken 171 should be familiar with asymptotes. Now, if you're not familiar with asymptotes, technically just think of it as this curve kind of just goes on and on forever. Even though to the naked eye, it's going to hit zero. But it's just never going to quite get there. But the probabilities are going to get so minuscule that it is like zeroed out. Now, who in here is taking calculus? No, but that's okay. Basically, an inflection point is where the curve changes curvature or concavity. And if you've taken calculus, you would know that that's second derivative. Now, am I teaching you calculus here? No. Basically, you go one standard deviation above or below the mean. That's where the inflection points are located. So, if you notice, for the mean and standard deviation, normal distribution can have any mean and any positive standard deviation. Standard deviation can never be negative. So the mean is going to give the location of a line of symmetry, and the standard deviation will describe how spread out the data are. So if you look at curves A and B, they both have the same mean but different standard deviations. The one with the larger standard deviation is obviously more spread out. Because remember, standard deviation of data means spread. How spread out are the data? And comparing B and C, those two have the same standard deviation. However, the means are located differently. Now, mean for this data can be negative, but generally we're only going to keep it positive. We won't get into negative data for this. So which of the curves is going to have the greater mean between A and B? Which would have the greater mean? A. How about the greater standard deviation? B. Remember, more spread out. The more spread out the data are, that's what we're going to get. Now, sometimes in statistics, now, let me ask here, did any of you actually take AP statistics in high school by chance? No, okay, I taught AP statistics, and the last time I taught it as AP was 8 years ago. I don't like the AP for various reasons, but one thing they had a real penchant for was having you estimate standard deviation, and I didn't like that, not one bit, because there was too much ambiguity with that. But we can definitely estimate a mean here. For instance, what can be represented by a normal curve? Well, test scores are definitely something that can be represented by the normal curve. IQ scores, heights, weights, hours playing video games, grade averages, all sorts of things can be approximated with a normal curve. And so we're going to see a standard normal distribution, and we're going to be working with that first. Now, the standard normal distribution is real easy. It's going to have a mean of 0 and a standard deviation of 1. In other words, the standard deviation is 1, and basically these marks are not only number of standard deviations away from the mean, they are actual z-scores. Now, what we're going to learn, probably today actually, is we're going to be able to take normally distributed data and convert it to a standard normal distribution. It's actually going to be a lot easier than you think. And calculator is going to be your best friend for that. So basically, this area under the curve is 1. And again, these z-scores can go on and on forever and ever. But generally, when we draw a curve, we go 3 below and 3 above. So that's as far as it typically goes. So this formula for z-score is the value minus the mean divided by the standard deviation. Now, this isn't your case at all, but ask anyone that has taken statistics, especially 10, even 5 years ago. I used to tutor this online through Chegg, and most of the people that I was tutoring in statistics were learning how to do this all on tables. I'm going to show you the tables, but we are not going to use them. Now, you might be saying, well, why are you showing us? Well, I'm kind of showing you how we used to do it back in the day. And believe it or not, when I took this course equivalent, more than 20 years ago, I taught myself how to do it with the calculator. So, what is this table that I'm talking about? Well, before we get into what the table is, here's the thing. Area to the left is the cumulative area. And basically, when the z-score is negative 3.49 or lower, the cumulative area is close enough to 0. And obviously, the cumulative area is going to increase as your z-score increases. And where z is equal to 0, that's the halfway point. Half the curve, the area should simply be a half. And 3.49 is where the area is close enough to 1. Now, do you have to memorize that 3.49 rule? No. But basically, if I took the area of the curve from negative 3.49 to positive 3.49, it will be sufficiently close enough to 1 to 4 decimal places. So, let me show you how we kicked it old school. This is what a normal distribution table looked like that most old school instructors forced students to use. And I mean, it's not a bad thing, at least not in my opinion. But how would we do this with the table if we wanted to find the cumulative area, that is the area to the left where the z-score was 1.15? Now, you're probably wondering, 1.15? How would I do that? Well, guess what? Ladies and gentlemen, get used to drawing these curves. Now, I'm not going to grade you on the accuracy of your bell curve. I'm not going to pull out a magnifying glass or a microscope. But in the middle of this curve, it is going to be a 0. I always like to do that. And we want the area to the left of 1.15. Now, and I'm going to shade that, although probably somewhat haphazardly. Now, of course, the table will tell us the answer, but we're going to use the calculator. Now, let's think about this for a second. That area is definitely greater than a half. So, guess what? Remember how we found binomial probabilities, geometric and Poisson? Well, guess what? Under that same menu, when you go to the distribution menu, what do you find? What is the first thing you see? Normal PDF. Now, we're not going to use PDF here. because this is always a cumulative one, we're going to use normal CDF. So, normal CDF. Now, it gives you a lower and an upper. Now, here's the thing. This negative 1e99, that is negative 1 times 10 to the 99th power. That is like negative a billion, trillion, a bajillion, I don't know. But do you actually have to type that extreme value in? No, I'm going to show you why in just a few minutes. But if you notice, yeah, so since there's no lower, right now they're using that. Technically, you could also construe it as negative infinity, but it's actually going to be a lot simpler than that. But for the upper, we're going to type in 1.15. And, not 1.14, but 1.15. Now, the mean and standard deviation are, for now, 0 and 1. Do not change those. Please do not change those. Now, when I go to paste it, I get 0.8749. Now, here's the thing. Do I actually need to do that negative 1e99 business? No. Since I have no lower bound given, believe it or not, I could go back here and get away with literally negative 10. And if you notice, the probability, those areas are precisely the same thing. So that's like 10 z-scores above or 10 z-scores below the mean. So if you do not have a lower bound like we have here, you would use negative 10 for the lower bound. Now, let's say if we were finding the area above a certain mark, what would we put in for the upper bound if we didn't have one? Positive infinity, but instead of that, we could just use positive 10. So negative and positive 10 are good bounds for that. Now, that's if we're dealing with the standard normal curve. Now, if we were not, you might want to make the lower like negative 1,000 or something small. But you don't have to go absurdly small. But here's the deal. Yes? That's right, we can. But yeah, we're getting ahead here. But yeah, you have the right idea. Yeah, see, this is how it used to be back in the day. We would have to use these tables. But I realized, hey, wait a second, I can use a calculator. You know, I don't think Dr. Rosen, I don't know. But that's how it's going to work. Now, if we wanted to find the probability that z is less than 1.27, basically less than or equal to 1.27 mean exactly the same thing. So I'm going to draw yet another normal curve. So I'm going to put 1.27, and I want the area to the left of that mark. So basically, I would just do normal CDF from negative 10 to 1.27. Now, by the way, if you notice, the last two parameters are 0 and 1. Those are default. In other words, mean and standard deviation are 0 and 1 unless you say otherwise. So, From negative 10 to 1.27, we get 0.8979 or 0.898 or 89.8%. Now, what if we wanted to find the area to the right? Well, the way I was taught is use the table to find the area to the left and subtract it from 1. Because the area under the whole curve is 1 or 100%. But we have a calculator that can do this for us ever so nicely. You know, of course, that 1.27 finds it there. But if I wanted to find the area to the right, obviously we know that this is 89.8%. Now, of course, this should be 10.2%. But let's do this anyway. I want you to normal CDF from 1.27 to 10, and I'll throw in that one, or anything higher. Now, 10 will not work if we're doing it directly with raw data. But we'll see what I mean by that in probably after the break. But if we normal CDF from 1.27 to 10, or anything larger, notice that I used 100,000. It really doesn't matter because I get 0.102. I get it that way. All right. Any questions on this? Just because I felt like it. Not to be a wise guy, but no, I could have put 10, and here's the thing. If I put 10, does that change my answer? Not at all, especially to 4 decimal places. Now, if you are working with raw data, such as maybe incomes or whatever, where you do change the mean and standard deviation, that's where you might not be able to use negative 10 and positive 10 for the lower and upper bounds, respectively. So, the calculator, again, is going to be our best friend here. This normal CDF feature, basically, it literally takes that equation that you found on page 1 and finds the area under the curve. Uses calculus to do that. But we're not using calculus in here. So, and here's the other thing. A lot of students have asked me, Mr. Jarrett, what do I do for the lower and upper bound? Draw a curve. You have to draw a curve. You need to draw your curves. Now, so these have, what I want you to do is find areas using normal CDF. And you can do the same thing for that one. I'll show you that in just a second. See, this is how you did it back in the olden days. If we wanted that z-score of 1.23, so what we had to do was, if we normal CDF from negative 10 to 1.23, we see that this is going to be 0.8907. In fact, what I'm going to do is this. I'm going to put this here Got to make that a little smaller. Now, if I wanted to find the area to the right, here's the thing. Back in the old days, you'd use the table to find your area to the left. You just subtract it from 1 to find the area to the right. But guess what? We have this wonderful graphing calculator. 1.23 to something larger. We'll just call it 10. I don't know. And we get 0.1093. So, now this is where it used to be real fun. If I wanted to find the area between two z-scores, I would have to find this whole region all the way and then subtract what I don't want. But the calculator. So here's the awesome thing. We have our lower and our upper right here. So we normal CDF that from negative 0.75 to 1.23. Never use normal PDF. The only time we're ever going to use normal PDF, by the way, is when we graph. If we graph it on the calculator. And if you notice, the answer from here, we're off by a 10,000th. And the reason we're off a little bit is simply because of rounding. I would accept either answer myself. So, it used to be a lot more entertaining to have to find the area to this and then subtract it. You know, yeah, if I did, that area, and then if I normal CDF from, negative 10 to negative 0.75, see, I get 0.2266, and yeah, basically, I could just subtract the two, do this, hit enter, and minus this, and we get 0.6640. But here's the thing. Lower, upper, call it a day, you've got it. Boom. That's all. You don't have to go through the whole process of finding the area that you don't want. So that's going to make your life a lot easier. And what we're going to do here is, after the break, we're going to find some areas after we draw some curves. So we want the area that is is it going to be to the left or to the right? To the left of negative 1.12. Terrible looking curve here, but yeah. So I always put 0 in the middle. So negative 1.12. So this area is going to be it's definitely going to be smaller than a half. So I could normal CDF this from negative 10 to negative 1.12. And again, ladies and gentlemen of the jury, use this negative button. Do not use the minus sign. Because what will happen, you will get an error and 0.1314 or 13.14%. Now, believe it or not, if you actually go to draw and shade norm, like negative 10 to negative 1.12, and you can even change the color if you have that calculator. See, yeah, it doesn't zoom in though. But, yeah. All right, so I want you to try the next one. Try these couple. So yeah, put a 0, negative 1.2, and 0.43. And again, I am not going to pull out a magnifying glass to see how far right or wrong you may or may not be. But here is negative 1.2 to positive 0.43. And we get 0.5513 or 55.13%. Give that to me as a percentage or whatnot. Get you the same thing. So let's look at greater than 0.98. So here's 0, and here is 0.98. See, after you draw these for so long, you'll get really used to them. So when I go to figure this out here, what am I going to put for my lower? 0.98. And what about for my upper? I could put 10 or anything higher. And I'll put 10.1. Why? I don't know. It doesn't matter. 10 or higher is good enough. 0.1635 or 16.35%. Now, those of you that went to high school in North Carolina, is the normal curve part of the Math 2 or Math 3 curriculum by chance? I don't remember. In Virginia, it was. They put it in the algebra curriculum, which I kind of liked. But I'll share a funny story with you for the next two. But negative 2.81, I think this is going to be a pretty small area here. So here is negative 2.81. So if I want to do this, what do I need to put for my lower? Negative 10. And then for my upper, I'll put negative 2.81. And I get 0.0025. Or basically 0.25%. Now, I always get a kick out of the last two. I have a funny, although it really isn't funny. Well, hopefully he graduated by now. So I had a student that had, when I started at Perry McClure, he took Algebra 2 with me and failed it because, well, he didn't do anything. And then he took it with my department head, failed it because he didn't do anything. Emails to his mother went unanswered. Phone calls went unreturned. And then second semester of his senior year, he's taking it with me. And this area is going to be 0.0522. And he's come alive, and I'm thinking, oh, maybe he's actually going to get off his butt and do this. Well, he tried to argue with me that for the second one, 1.4 to 1.8 should be the exact same probability. And I told him, well, it's not. Because, the area under the curve, because I had to point out, the locations are too different here. And it's going to be 0.0448. And, of course, we finally heard from his mother. What we're going to do here is we're going to do the true percentages versus the approximations. So if we went within one standard deviation, we would approximately have 68% of the data. If it's within 2 standard deviations, we would be going approximately 95% of the data. So the third standard deviation, what would the approximation for that be? 99.7. So here's what we're going to do. We are going to find the actuals. So if we go within 1 standard deviation, -1 to +1, and let's normal CDF that. Remember, within 1, so it's 1 standard deviation above and 1 below. And we get 0.6827. Or 68.27%. Now, if you were to write out that phrase, 68.27%, that takes a long time to say. It's good enough to say 68 for approximating. Now, let's do the same thing for 2 standard deviations. We go 2 below and 2 above. 0.9545. Or 95.45%. And let's go 3 above and 3 below. 0.9973. Now, just for fun, let's go 4 standard deviations. Let's see what that is. Would we ever do this in the real world? No. 0.9999. Or literally 99.99%. 1/100th of a percent is, 4 standard deviations. So here is a good question. Where are the inflection points located on a standard normal curve? You might see this on my lab. I wouldn't put this on a test. But how many z-scores are they located? What were the z-scores where the inflection points are? Nope, just 1. Positive and -1. They're right up here. Yep, positive and -1. All right, now, I want you to answer the next set of questions, and then we'll go to the supermarket question after. I want to find the probability that z is greater than -1.21. So it's going to be pretty large, definitely larger than a half. .8869 or 88.69%. So problem like this, we're going to find the area between these 2 marks, 0.82 and 2.12. And no, I do not have an OnlyFans or anything like that. Don't keep... I know, like when I subbed at my wife's school, someone's like, oh my God, so-and-so has an OnlyFans. Like, no, they don't. Because that's going to come out. That's going to make its way out. 0.82 to 2.12. 0.1891 or 18.91%. Not a bad deal. Now, which of those two curves is going to have the smaller standard deviation? That's right. How about the smaller mean? Excellent. Now, this is going to be a good bridge to what we're going to get into. A survey indicates that, and one thing I failed to mention was that it would follow an approximate normal distribution. A shopper spends an average time of 68 minutes with a standard deviation of 18 minutes. So we're going to draw and label a normal curve with both shopping times and the z-scores underneath that. So we're going to go 3 z-scores above and below the mean. So how do we do that? Well, 68 minutes, that is an hour and 8 minutes to you and me. X is going to be the time spent. And underneath that, I'm going to put my z-score right now. What is the z-score corresponding to the middle? 0. That's right. Going to be a 0. Now, the standard deviation is 18 minutes. So we will go in increments of 18 minutes above and 18 minutes below. So do you want to start going lower or higher? So one standard deviation below would be how many minutes? 50 minutes. How about 2 standard deviations below? And how about 3 below? 14. Now, what would the z-score be corresponding to a time of 50 minutes? -1. How about 32 minutes? And 14 minutes? Now, let's go above the mean. One standard deviation above the mean is, and a second one would be, and a third one, and of course the standard z-scores are 1, 2, and 3. Now, I want to emphasize something. I've always written this out, and students would think, oh, I have to write this out too. So I want to say this, you do not need to write this out every time. But if I wanted to find like the z-score corresponding to 104 minutes, we know it's 2. But if we do 104 minus 68 over 18, that does equal 2. That is just an example. You do not need to write this out. Now, for instance, so let's think about this for a minute. Yeah, when I go shopping, I try to keep my time in the supermarket here. When I was living with my parents and say I'm running down to Walmart, my mother would be like, oh, I want to go too. It turned into something like this. If we ran into a band parent, we would be at a z-score of 3 or above. I mean, love the lady, real nice, but God, she just doesn't stop. Well, she's unfortunately no longer with us. Yeah, I mean, she was a nice lady. Don't ever get me wrong, but my God, if you ran into her, cancel your plans for the next 3 hours. That's basically what it came down to. So, what we're going to be doing here, and if you notice, we drew one curve with the time spent and the z-scores underneath it. So even though we're going to do similar examples here, I want you to find the z-score corresponding to 30 minutes for me real quick. All right, so if we do 30 minus 68 over 18, here's the thing. I picked 30 just as a random value. So that's negative 2.11. So if you notice, yeah, 30 minutes is right about here. And that is between -2 and -3 standard deviations. So it kind of gives us a spatial view of where this is located. 30 minutes. You got 30-minute guarantee. You ever hear about that Domino's guarantee, 30 minutes? Domino's, back when I was a kid, if you ordered from Domino's and it wasn't there in 30 minutes, it was free. And because and here's the vicious thing, it came out of the driver's pay. And so drivers were driving like crazy. And after a few people get killed, it literally makes them change their mind. I mean, I can't even see how that was legal in the first place. But it was. Now we're finally going to do some actual data. We're going to look at some raw data for where we will find z-scores and the area under the curve. So this could be an example of like maybe SAT scores, where the mean is not 0 and the standard deviation is not 1. But what happens is, this is going to have a z-score of 1 very easily because, number one, it's how we calculate it. But basically, what they do is they find the area, they convert it to a standard normal distribution where the z-score is 1. Now, am I going to have you doing 2 different curves? No. Just draw me one curve, please. That's all. But I'm also going to show you both ways that this can be done on your calculator. See, this calculator is like one of the greatest inventions ever, in my opinion. So the area is going to be simple to find. Basically, you would just normal CDF from -10 to 1. But I'm also going to show you how we can modify things and do it a little bit more directly. But we'll get to that probably a little later. 0.8413 or 84.13%. So I'm going to expect you to find z-scores, not for every single problem. If you notice on the labs, they'll say you have to find the z-score for this directly and write me a complete sentence too. I don't ask that for every question, but you'll definitely see that for the unit test. I'll be honest, the unit test is going to be like 1 or 2 curve questions, and basically it's going to be 20 questions off of a normal distribution. You'll see. So in this supermarket example, here's the thing. Now, this is very old school in the sense that they actually calculated the difference here. Note the subscripts with the z-scores. I prefer to use the actual time, where the mean is, what was the mean? 45 minutes and the standard deviation of 12 minutes. But I would have preferred to use z sub 24 and z sub 54. Now, basically, we find the 2 z-scores. And See, this explains how to do it with the table. But guess what? Are we using the table? No way. We're just going to normal CDF this bad boy. And negative 1.75 to 0.75 with a standard deviation of, with a mean and standard deviation of 0 and 1. And we get 0.7333. Now, would you like to see the other calculator trick? It's really not much different, but I'm going to show it to you anyway. So, you ready? Now, what were the shopping times in question? 24 and 54. Now, what was the mean and standard deviation? So I'm going to put this up here somewhere. And actually, I'm going to put it over here, even though I made it smaller. But we have changed our mean and standard deviation. Look at that. Now, does that mean you can forget about how to calculate z-scores? No. You still got to show me that you can calculate a z-score. I'm still going to ask you to show me how to do that. But guess what? You have something a little bit easier for MyLab. Your MyLabs became a bajillion times easier. But wait, there's more. I forgot something. StatCrunch is coming back. So we're going to go to StatCrunch. And let's see here. I'm going to go into Moodle. See, I love this stuff. All right, MyLab. And mastering tools. Yeah, allow and continue. Sometimes you have to do that. And we're going to go to StatCrunch. And well, here's the other good thing. This is on video. So I'm just going to go directly to StatCrunch and open it up. That should be a serial, StatCrunch. So you're probably wondering, okay, what do I do here? Well, if you go to calculate, go to Stat Calculators and Normal. Now, I am going to blow this up, even though it might be a little hard to see here, but right now the mean is 0 and the standard deviation is 1, and I want to go between. So if I choose negative 1.75 to 0.75, I get this. Now, what if I changed my mean and standard deviation to 45 and 12? 45 and 12, 24 and 54 minutes. You are going to love this. Look at that. And how can you copy? Well, you can literally just copy the image and you can paste it into your thing. Of course, you might have to make it smaller, but that's how it all works. Pretty awesome. So, what if I wanted to be in the store more than 39 minutes of time? So, here's the thing. If I wanted more than 39 minutes, now of course, this is how it's done finding z-scores. Now, let's say I go back to normal CDF this, and I want 39 minutes. Now, obviously, I can't make the upper 10. So I would have to make the upper something really big, like maybe Okay, 10,000 might be overkill, but 0.6915. So in other words, yeah, if I did directly on calculator, you would normal CDF from 39, and we'll call it big, with 45 and 12. So let's just see here, let's see. Yeah, 10,000 minutes. That's, God, how many hours? That's forever. 1,000 minutes. That's a lot of hours still. Now, 100 just might not be enough. Now, with a standard deviation of 12, it probably is. To 4 decimal places, yeah. But notice that I said big. Just do it that way. Now, this is a really good example here. Let's say 200 shoppers came into the store. How many of them would you expect to be in the store more than 39 minutes? Well, the expectation is n times p. And you're probably thinking, wait a second, doesn't that sound familiar? Doesn't that sound familiar? N times p. Where did you see that before? With a binomial distribution. And you might be wondering, but wait a second, this is normal distribution. Believe it or not, in large numbers, the binomial approximates to normal. Now, do you really have to know that? No, but that's how it works. So yeah, 200 times 0.6915 or 138 shoppers. That's how many you would expect. But that's why we can use the n times p. That's why we can do that. All right. So finding z-scores, and again, if you look at your labs, you'll see that on some of these, you don't have to find the z-scores directly. I mean, you can just use a calculator and call it a day. But there'll be some where I'll say, find the z-score. So basically this explains what we just did with the normal curve. Normal CDF, whether you change the mean and standard deviation or not, you should get the same exact values as you got before. And that was what, 0.7333, yeah. Yeah, but make sure if you're doing it for z-scores, it has to be 0 and 1 for the mean and standard deviation, please. Now, first thing I want you to do is, let's say the heights of men are approximately normally distributed with a mean of 69.3 and a standard deviation of 2.4. Basically, the way your problem will look for anything like this is the first thing you're going to do is draw a curve. And we can answer some questions and whatnot. So x will be the heights, and underneath that I'll put the z-scores. So the mean height is 69.3. We'll go 1, 2, and 3. I probably should have drawn this a little better, but again, this is not art class. So one standard deviation below would be 66.9, 64.6, and 62.2. And then if we go above, let's see here, that would be 71.3, 71.7, 74.1, and 76.5. So yeah, 0, -1, -2, -3, 1, 2, and 3. So, what percentage of men have heights that are below 69.3 inches? Well, do you even need to use a calculator to figure this one out? No. What is it going to be? 50% of the men. 50% are shorter, 50% are taller. Yes, I know there are men that are 69.3 inches exactly, but we're just going to go with it that way. So yeah, 69.3, we're going below. Yeah, we don't even need a calculator. So, for this one, even though I didn't say so, I want us to find z-scores. And generally, and we're going to see what happens when we do z-scores if you don't round them. But I believe I would have it written on your lab that you'd want to round the z-scores to 3 decimals. I'm going to be as specific as possible with all this. And we'll do a complete sentence for good measure. Here is 69.3, here is 68, and here is 71. So one of those z-scores is going to be negative, and the other is going to be positive. And standard deviation was, again, 2.4. Yeah, 71 inches, that's 5'11". Over 2.4. And what I'll do is I'll just do it for 71. So we have negative 0.542, and we have 0.708. So here's the thing. Here's something to watch for. So what I'm going to show you here is, let's say someone said round the z-scores to 2 decimal places. So if we did that, negative 0.54, not natural log, that's really bad, to 0.71, but we're back to 0 and 1. We're back there, and we get this. Now, let's round that to 3 decimal places. And let's see if it changes our answer. Not really. But here's the thing. By doing this, rounding the z-score, the more you take the z-score, the more accurate it's going to be. And yes, it is the most accurate would be to do 68 to 71 with a mean of 69.3 and 2.4. But what happens here is, yeah, this third version is the most accurate one. Now, I would accept either one. you know, so basically, yeah, 0.4666 or 46.66% of men have heights between 68 and 71 inches. Now, that's a complete sentence. You'll be asked for a complete sentence every so often. You'll definitely have those on your case study. All right, how about men going above 74 inches? Figure. So let's see here. Obviously, 74. How tall is 74 inches? 6 foot. 6'2". That's my height. So here's what I'm going to do now. If I go to normal CDF this, 74 is my lower. Uh, I could probably get away with 100 inches. 100 inches is like, how tall? 8 feet 4. I think the world's tallest man in recorded history, I'd have to look that one up. But yeah, whether I did 100 or 1,000 inches, it's going to be 0.0251 or 2.51%. Now, before we do that, we can go to StatCrunch and even chug it into there. And you would go to standard 69.3, 2.4. And this time we're going to go above 74. And there it is. All right, so I'll tell you what. We'll go ahead and stop it here. Get approximately normally distributed with a mean of 337 pounds and a standard deviation of 14 pounds. So you want to answer a couple of questions pertaining to that. Let's do this first one here, and so here's the thing. You could just use the calculator for this one and flat out get away with it. But what I'm going to do here is I'm going to figure out the z-scores and everything for this. So yeah, 337 pounds, we're going to go between 320 and 330 pounds. So what we're going to do here is we want to go ahead and figure out what the z-scores for this are going to be. So both of these z-scores are going to be negative from what we can tell. Because they're both below the mean. So yeah, if we took 320 minus 337 and divided it by 14, to be a lineman, you got to be pretty big too. Now, one of the downfalls with what I'm doing here is it's actually going to do this. It's going to leave it as a fraction. Now, what I'm going to do here is get a decimal. It'll be negative 1.214. And for 330 pounds, we're still going to be negative here, but not as extreme here. Yeah, 330 minus 337 and dividing that by 14, oh, we get negative 0.5. So then what we get to do is find the area using normal CDF. So yeah, negative 1.214 and negative 0.5. Negative 0.5. And we get 0.1962 or 19.62%. All right, now I want you to figure out the percentage of linemen that are going to be over 360. All right, so let's go over 360. Yeah, that's pretty heavy to be a lineman. So you have 337, you have 360. So that Z-score is definitely going to be positive. Now, one thing we can do is instead of having to actually figure out the Z-score, we could actually enter 360 for the upper limit. Now, of course, realistically, yeah, I mean, 1,000 would be good. I mean, there's nobody in the NFL playing that's 1,000 pounds. And 14, and we get basically 0.0502 or 5.02%. Now, what percentage of linemen are going to be below 310 pounds? Well, let's kind of figure that out. Now, I'm going to do this straight away in the calculator here. So, when I do this, is my lower or upper going to be 310? When I go to normal CDF, we want to go 310 or below here. So, will this 310, is that going to be the upper or the lower bound? That's going to be the upper bound. Now, for the lower bound, realistically, I mean, yeah, we could put 0, and that would probably be enough. Or one thing you could get in the habit of doing is like a really, really large negative number, and we get 0.0269 or 2.69% of offensive linemen are going to be below 310 pounds. All right, so let's suppose we have 1,024 active linemen in the NFL. How many of them would we actually expect them to weigh below 310? Well, remember this. That is N times P. And we already calculated the probability. And of course, we're going to round this to the nearest person. Times 0.0269. And we'll just round this to the nearest person. So 28 of them. So not very many linemen are going to weigh below 310 pounds. Offensive linemen. Defensive linemen, you have some heavy ones, but you also have had some pretty scrawny looking ones at first that would actually bulked up. Like, I'll give you. So now we're going to add yet another dimension to all of this, where for instance, what weight would be in the top or bottom or middle percentage of heights? So we've got to start up kind of a new section here, finding z-scores given various probabilities. So what if I gave you the area and you would need to find the z-score? Well, that's pretty easy enough. You would draw a bell-shaped curve and identify the region. Now, yeah, imagine what this was like before calculators. It was not very fun to do without a calculator. But now, with the calculator, our lives are going to be a lot easier. So in the previous section, we'd have data which we would convert to a z-score and then convert into a probability. But now, what would happen is I'm going to give you a probability, which in turn you would convert to a z-score, which in turn you would convert to an x value. But one good thing is we could actually skip that technically by using technology, but we're going to do it both ways. So, if we wanted to find the z-score that corresponds to a cumulative area of 0.3632, this is the area of 0.3632, and here's the thing, you would be looking at this, looking for this on the table. Now, of course, we are not going to ask for like the bottom 36.32%. Instead, we would say maybe bottom 35% or whatever, but what we would have to do is kind of look for the two values that it's between and kind of, go between them or whatever. But we don't really have to do that here. We're going to use technology to find it much more precisely. Now, if you go into the distribution menus on your calculator, under normal CDF, we see inverse norm. So make sure you go there, inverse norm. Now, those of you with the black and white calculator don't have the luxury of left, center, and right. But you are allowed to use one of these on a test day or whatever. But I'm going to enter 0.3632. And right now we're keeping it standard normal. And since it's being kept as standard normal, we're going to keep the mean and standard deviation at 0 and 1. And still, it's going to be left-tailed. In fact, it's always going to be a left tail. And we get negative 0.35. So that's simply how this is going to work. Now, if I wanted to find a z-score to the right, like if I wanted, say, a top certain percentage, like top, we're using this because this is right on the table. Like the top 10% or top 10.75%, in reality, we wouldn't do that. But we're strictly going by, like for the table here, if it's 10.75% to the right, it's 89.25% to the left. And the reason I used that was because that's what because it's right on the table. But if I go to inverse norm and 0.8975, oh wait, it was 0.8925, I'm sorry. 0.8925. Yep, that z-score is going to be 1.24. Now, the downfall of the table is that, yeah, it's not going to have other values. You're going to have to kind of go between. But that's okay. Now, let's say I want to find the 75th percentile for a piece of data. So, would the z-score be positive or negative for that? Now, you might want to remember what is, 75th percentile means it's going to be 75% to the left. So basically, you're going to find a z-score by doing inverse norm of 0.75. And here's the thing, the z-score is going to be 0.675. So that represents the 75th percentile. Now we could have also found that, if that z-score could then be converted to normally distributed data, such as a test score, height, weight, or whatever. But this is the other big part of this unit. So let's say I want the z-score corresponding to the top 65%. And middle 95, you're going to do that. Top 65%, very simple here. Basically, it is 65% to the right. Now, if you have a black and white calculator, well, I'm still going to show you 65% to the right. But if it's 65% to the right, top 65%, it's not really realistic, but we'll just go with it anyway. That means, what is the area to the left? %35. Now, here's the deal. I'm going to show you both ways. 0.35 to the left. And again, this is all on the calculator. And if I did 0.65 to the right, it should give me the same thing. Needless to say, that z-score is negative 0.3853. Now, why would I ask for top 65%? I would have rather said bottom 35%. I would have rather said it that way. Now, here is something I want you to do. So we inverse norm to find this. I want you to normal CDF from negative 10 to negative 0.3853. And then I want you to normal CDF from negative 0.3853 to positive 10. The normal CDF from negative 10 to negative 0.3853. What did that give you? 0.35. What about the other one? Let's see here. We normal CDF negative 0.3853 to 10. 0.65. This all comes together here. Now, the reason it's not like exactly right on the money is because this z-score is only 4 decimal places. I mean, we could take that z-score even further if we really wanted to, but in all honesty, 3 decimal places is enough here. But basically, here's how it works. This part that we just did with the normal CDF, you don't need to do that, but I'm just kind of showing you that, hey, this is how it works. But if we want to find thresholds like bottom 35% or whatever, that's when we would be using inverse norm. Now, middle 95%, that's a goodie. Now, of course, you can use center 0.95 and it'd be just as well. But those of you with the black and white calculators, I'm going to show you how we kicked it old school. And StatCrunch can also be utilized for something like this. So if I have 95% in the middle, what percentage of data do I have on either side? 2.5%. 2.5% and 2.5% here. Now, the percentile or area is 2.5, 2.5 percentile or 0.025. And this mark, what is the area to the left of this mark? 97.5%. And 0.975. The difference between these two is 0.95 or 95%. So here's the deal. If you inverse norm each of those, 0.025, we take it to the left, that z-score is negative 1.96. Now, without even doing that on my calculator, but I'm still going to do, I didn't want to do that. .975, we get positive 1.96. And so anytime you would be asked for like middle whatever percentage, here's the thing. It's going to be it's symmetric. Now, of course, those of you with the newer calculators have the luxury of taking 0.95 in the center. And it gives you the two z-scores that way. Now, but the black and white ones do not do that. But again, you have access to these color ones in class. That's why I suggest, even though you borrowed we just don't have enough of the color ones to lend out to students for the semester. Just the way it goes. But this can also be done on, you guessed it, StatCrunch. All right, so if we go to calculators and we choose, normal. Here's the thing, standard normal, if I wanted the area to be like 0.975 and I could choose to the left or to the right, what happens is I compute that and it gives me the z-score this way. Now, if I went in between and I changed this to 0.95, by computing that, see, I get my z-scores that way. So basically, you can enter the desired area, or if you want to find the marks that you need, or you can enter the desired z-scores or whatever and get the area, which is kind of what we did last class. Now, Critical values. Critical values are going to be a new thing. And here's the other thing with critical values. You are going to see critical values yet again in the next unit. Now, it's going to be a z-score that separates unlikely values from those that are likely to occur. So this expression, z sub alpha, denotes the z-score with an area of alpha to its right. Now, in the next unit, we're also going to learn the t-distribution, which I'll be dead honest with you, it is very similar to the normal distribution. But we don't do, this is actually chi-squared. I would really love chi-squared. I really enjoy it. And F, but that's in ANOVA. See, that's usually done in Stats 2. And God, I would love to teach Stats 2. So basically, if you have a z here with a 0.05, the area to the right of that is 0.05. Now that means you're finding the 95th percentile, which is 95% to the left. And we can find that on the calculator, 95th percentile for the inverse norm. And of course, we're going to do left. We're going to keep her left-tailed, 1.645. So, since this has an area of 0.025 to the right, this is 0.975 to the left. And we've already figured that out. The z-score is 1.96. Now, these last two are just kind of off the wall, but you'll see why we do those. So I'm going to give you a moment and let you try those. It's going to be a z, and that's 1% to the right, or the 99th percentile. In other words, this is top 1%. So that's a good question that you're going to be asked. Top 1% of something. And we can find that very easily, or the 99th percentile. .326. Now for this is the 80th percentile, and if it's 80% to the left, what is the percentage to the right? 20. Top 20%. I always like to share the story when I went to my first college orientation, they were saying, all right, those of you that were in the top 20% of your graduating class, stand up, and I didn't. And my mother's nudging me. She's like, Patrick, stand up. I'm like, Mom, I wasn't in the top 20%. She's like, you weren't? I'm like, no, I was 24th in a class of 100. That's not top 20%. She's like, come on, it's close enough. I said, no. Z is going to be 0.842. I don't know. Top 10%, and what percentile is represented by that? 90th. Typically, when you see things, there is no such thing as 100th percentile, except my wife would say the size of your head. Because I don't know, she's like, I don't know if there's anybody with a head bigger than you. I said, there probably is. And yeah, so the z-score is going to be 1.282. Now, 42nd percentile. Why did I ask that? I don't know. But that means it's 58%, above that. and this would be 69% above that. So the 42nd percentile and the 31st percentile are going to be below average. Hence, they will also yield negative z-scores. The z-score is negative 0.202, and the 31st percentile would be negative 0.496. So why do we learn all this? Just to torture you? No, there's no such thing as torture in statistics. We have applications that are going to deal with this normal distribution stuff, such as test scores, weights, all sorts of good stuff. And I'm really trying to find some more entertaining examples, like gaming times or whatever. And you can relate applications to the standard normal curve. So typically, like for any major test, yeah, test scores are approximately normally distributed. Now, who's ever heard of the GRE test? The GRE test is basically the SAT for college grads. It's to get into grad school. And I had to take the GRE to get admitted to the Masters in Math at James Madison. Well, so I had to do a math. See, they change the test every few years, it seems. But, for the math score, I was in the 99th percentile. I wasn't really surprised, because it's like it's better than 99% of college graduates, not just math majors. For the reading portion or the verbal, I was in the 58th, which means I did better than 58. Now, my writing sample was in the 9th. Now, if I were applying to grad school to become a writer, yeah. And yeah, that was just not good. So, we're going to put it all together, finally. So, SOL scores, that was the state test in Virginia. I could probably use something a little more entertaining than this, but oh well. They're approximately normally distributed with a mean of 456 and a standard deviation of 45. So for questions A, B, C, and D, now starting with E, we're going to employ what we just learned. So yeah, score of 400 or higher. That's passing. So I'll let you figure that one out. All right, so the mean is 456. Passing is a 400. And let's just do it the whole way through. Let's just do the full Monty. Let's figure out the z-score. Now, will the z-score for 400 be positive or negative, by the way? It's going to be negative because it's below average or below the mean. So 400 minus 456 over 45 and negative 1.24 repeating. And so here's the thing. So then I'll normal CDF that from negative 1.244 all the way up to 10. And I get 0.8933. Or 89.33%. All right, so we'll go and take 75 and 400. Now, the significance of that, FYI, was that was what we called expedited retake. So keep in mind, again, the mean was 456. So yeah, 375 and 400. So we already know the z-score for 400, which is really nice. Negative 1.244. So let's figure out the z-score for that, for 375. 375 minus 456 and divided by 45. And we get, oh, negative 1.8. So we have our lower and our upper bounds right there. So since we have our lower and upper bounds straight up, let's do it. So we normal CDF from negative 1.8 for the lower and negative 1.244. I mean, I could make that forever, but we get 0.0707 or 7.07%. Now, I've had many students in the past that would get a, what happens if I get a negative probability? Number one, this isn't actually calculating a probability, but what it's doing here is it calculates a percentage or the area under the curve. And for some reason, if I got my wires crossed, which you really shouldn't, but I'm going to just kind of demonstrate to you that this is what happens. That's going to be negative because, normal CDF is using calculus to figure out the area. But the other thing I could have done is for normal CDF, yeah, I know, I'm going through the whole idea here. 375 to 400 with a mean of 456 and a standard deviation of 45. See, that's how you can get it straight up. All right, what percentage of students are going to get above a 500? Now, 500 is a passing advanced. So here's what I'm going to do. How about I just do it straight up? Do I need to figure out the z-score? No. But would 500 be the lower or the upper? 500 is going to be the lower. And here's the thing. I don't really have an upper, so I'll just make it some big giant number. Technically, it is 600, but 600 is not enough. That's a perfect score. 0.1641 or 16.41%. Now, 2,000 students, 2,000 students have taken Algebra 2 with me. How many of them would be expected to score above a 500? Well, that's that N times P deal. 2,000 times 0.1641. And of course, we'll round this to the nearest whole number. And we get 328. All right, now, this is where, so basically, yeah, we already learned how to do this, from A through D. We learned how to do that in the last class. Starting with E, we're going to figure out some values here. So, what score represents the top 5% of scores? Top 5%. So, we're going to do this entirely brute force. So keep in mind, yeah, I want this to be 5% inside of here. Now, you can get a z-score by doing this. You have 5% to the right, or what percentage to the left? 95% to the left. Either way, you'd get the same thing. So here's the thing, and yes, if you're keeping score, you can see that you can change the mean and standard deviation. And I'm going to show you, yeah, you can in fact do that, but let's do it the long way just once. 95% to the left, and this z-score is going to be 1.645. So, using this formula, we have the z value of 1.645, and that will equal x minus 456 divided by 45. You'll have to do this one time on any lab or unit test. It demonstrates that you can do some math here. So what can I do to both sides of this equation to help me solve for x? Multiply both sides by 45. So we will take the 1.645 and multiply it by 45. And we get 74.025. I would say nearest whole number for these. And I was rather non-specific about this, about rounding on these, but I should be, on the labs, I think I'm specific enough. X minus 456. So what do we do to get x? We're going to add the 456. And here's the thing. So if we add 456, we get 530. So basically, the top 5% of scores is 530. Now, 530, is it going to be or higher or lower? Or higher. The reason it's or higher is because it's the top. If I asked for the bottom 5%, you could say or lower. Now, and yes, if you go to the inverse norm yet again, we can change the mean and standard deviation. And it'll give you the score. Now, here's the thing. It's going to be a little bit different from what we calculated here because it takes the z-score from the curve to all of the decimal places. But that's how you can do that straight up on the calculator, and believe it or not, on StatCrunch. I could change this to 456 and a 45, and if I want the area to be 0.05, There's my score. All right, so I want you to find top 10%. All right, so top 10% of scores. So here is top 10%. And what I can do here is obviously top 10%, the percentile is 90%. So what I can do here is I could even do this top 10% and to the right. And yeah, is it cheating? I don't think so. 514. So it's going to be 514 or higher. Now, was this higher or lower than the top 5%? It was lower. Now, how about the top 1%? That's going to be pretty far up. 75th percentile and then middle 50%. So here we go, 1%. Now, that would be 99% to the left. Now, top 1%, here's the thing. If you entered 1, it would not give you anything. Well, yeah, because it's an overflow. Remember, it's got to be a decimal. And remember, and here's the thing, yeah, you got to make sure you know how to convert these decimals. So yeah, top 1%, which is 561. So yeah, 561 or higher. Or bottom, 99 percentile if you have the black and white calculator, which is maybe what I should just be doing the whole time anyway. 99th percentile. Yeah. But see, you get the same thing no matter what. All right, 75th percentile. 75% below it, 25% above it. Now, 75th percentile is a mark. You don't need to say or higher or lower. You would just say, whatever it is. The 75th percentile is 486. Now, I'm going to let you play middle 50%. So middle 50%. Now, let's look at this here for a second. So if we draw this, middle 50%, and that's a typical metric where they'll measure scores. So middle 50%. Now, what percentage is on either side? 25%. So I'm going to pretend we're still using the black and white calculator. I don't know why, but I'm still going to do that. This is the 25th percentile, and this is the 75th. The distance between 25 and 75 is 50. But, I could find the z-scores that go with that. But instead, I'm going to find this. The 25th percentile is 426, and the 75th percentile is 486. So basically, 426 to 486. Now, if you normal CDF that on the calculator, it might not be as precise as you'd want it to be because, we rounded to the whole number here. So for a LARF, so yeah, if we actually went ahead and figured out the middle values and did center, here's the thing. We get those values, and let me see something here. Statistics. No. Not there. Test. Let me see here. Lower. Nope, it's not defined. Okay, that's okay. So maybe there's not a direct way to do this, and that's even better. But again, that's okay. Okay, so yeah, we can't really do it directly here. But yeah, if I normal CDF from 426 to 486, here's the thing. 456 and 45, I get 49.5%. But if I went backwards and did 425.65, if I did decimals here a bit, 425.65 and 486.35. Yeah, see, I'm much closer to that mark. So that's how it's all going to work. Now, one of the key ingredients to doing this is grading on a curve. Now, what a lot of students don't realize, and it's okay, because here's why. Typically, in a college class, yeah, we don't really grade on curves. What usually happens when teachers curve is they literally change the cutoffs arbitrarily. And because I remember, for instance, when I took organic chemistry, yes, I took organic chemistry. I was going to try to double major in math and chem, but yeah, it wasn't in the cards for me. And on day one, I remember the professor said, so this is going to be the curve, like 82 will be an a B will be 68, a C will be 49, and a D will be 32. And we're thinking, oh my God, this is great. But when the average on the tests is like 48. So yeah, basically what the professor did was he took data from many, many years and came up with those cutoffs. But what a lot of instructors have done in past years is, yeah, they would take data and they would say, okay, based on this, top 10% are going to get A's, then this percentage are going to get B's, and then C's and D's and F's. So, yeah, so basically what'll happen is, let's say the mean for this is a 48.3 and a standard deviation is 6.8. So, our first thing that we have to do is to draw the curve. So, highest 10% are going to get A's. Now, what percentile is represented by this mark right here? '90th percentile. Now, we could probably figure out everything after this fact here. And then the next 15% down, and I should probably say down from there, are going to get B's. So this mark here, if it's 25% to the right, what percentage is to the left of it? 75th percentile. So these are your B's. Now your C's, what percentage are going to get C's? 35%. So 35, 15, and 10 adds up to 60, 60 to the right, but to the left we have 40th. That's the 40th percentile. And here's another way to look at this. we lost 15%. Well, we didn't lose 15%, but we used up 15%. 90 minus 15, 75. 75 minus 35, 40. And then 25% are going to get D's. And what is the percentile mark for this? 15th. And that means what percentage are going to get F's? 15% are going to get F's. So now you have a series of cutoffs to find. But here's the best thing. The calculator is right there for you. You're going to just use inverse norm and figure out those cutoffs. So, once we figure out all the cutoff marks, what's going to happen next is we'll be able to figure out our grading scale. We'll round those to 2 decimal places. So we can start from the bottom, inverse norm 0.15. Now the mean is 48.3 and the standard deviation is 6.8. And again, we're back on left. And this is going to be 41.25. So F would be below a 41.25. Now a D, the low end of a D is 41.25, but let's figure out the high end of the D. The high end of the D is 40th percentile. So we go back to, yep, inverse norm yet again. The 40th percentile, and it's 46.58. Now for a C, we want to figure out the 75th percentile. So now some of you might be thinking, wait a second, we're doubling up here. Well, let's be honest. If I were a professor, yeah, I would make a D a straight up 41 and maybe make a C a 47 or a 46. So we've got to figure out the 75th percentile. And let's see what that's going to be. The 75th percentile, 52.89. So a B, yeah, starts at a 52.89. And then lastly, we got to figure out the 90th percentile. So 0.90, and that's 57.01. And an A would be 57.01 or higher. Now, yeah, in a class like this, yeah, I mean, we're going to do other examples, not necessarily as they pertain to grading. But what we're going to do, so here's the thing. This is how it used to be, like what some instructor, even school teachers, like, yeah, if they grade on a curve, basically they decide, like, okay, the top 10% of scores are going to get A's, this percentage are going to get B's, this percentage are going to get C's, and so on. I remember one semester in Virginia, we had to wait for an exorbitant amount of time to find out results for the state test. And I said, what's taking so long? Because scores usually came back the same day because it was always a multiple choice test. And what we found out was we were one of the first schools to take that year's test. And so they said, well, we got to determine what the cut score for passing and failing is. Wait a second. You determine that in advance. So what you're doing is you're rigging this. Yeah. See, yeah, it was really just incredibly stupid. No, that's all right. So that's how grading on a curve really works. Now, I've been in classes where, yeah, we've been graded on a curve, not like this, but I remember it was a shop class. It was called Power Technology. Greatest teacher ever, old Mr. Grove. So here's what I'm going to do. I'm going to make it top 11% get A's, and the next 14% are going to get B's, and the next 51% are going to get C's, and we'll leave it with D's and F's. All right, I want you to find the cutoffs based off of this, please. That's top 11% are going to get A's because I want to give out as many A's as I can. So here's your A gang, the A team. And then 14% are going to get B's. So, and then 51% are going to get C's. A lot of people get C's. And then 18% are going to get D's. And then the rest are going to get F's. So we can figure out what is that percentage that are going to get F's. Well, 51, 14, and 11. 94% are accounted for here, so basically 6% are going to get F's. See, I want to give as few F's as possible. Now, this is the 6th percentile. This would be the 24th. This would be the 75th and 89th. Now, before we punch these up and figure them out on the calculator, for the 6th percentile, what do you have to type in for the area? .06. Good. Because if you did 0.6, that's the 60th percentile. So let's see what we've got here. Sixth percentile. Yeah, 61.3 and 8.8. 47.62. So then we'll do the 24th percentile. .08. The 75th percentile. .24. And then the 89th percentile. .09. So basically, an A is 72.09 or higher. I would probably have made that a 72 myself. A B would be 67.24 to 72.09. A C would be 55.08 to 67.24. A D, ooh, yeah, 47.62 to 55.08, and an F would be below 47.62. So that's a couple more of these grading curve style problems here. This time I'm going to give you a curve that is symmetric, where the middle 50% are going to get C's, and the next 15% each up and down. So 15% above that and 15% below that are going to get D's and B's, and the remainder get A's and F's. So this is a curve that's evenly split here. So a couple of other things worth noting here. So of course, your first lab assignment is due on Wednesday. The second one will be due Monday. We're actually a little bit further ahead than I thought we would be, because normally the normal distribution takes a little longer. Now, I'm not going to move the test back or up or anything, but what I could do is I might actually start the next unit just a day ahead. So we'll have that. Now, your case study is also posted. That will be due the day after you take your test. So when you take, so yeah, that'll be due. So you do have an extra day, so to speak. Everything you'll need is on there. There's help documents that can get you squared away on that. You know, you'll have the test on Monday the 28th. That's 2 weeks from today. So we'll have that. All right, so just to kind of get you started here, you know, middle 50%. Now, of course, the black and white calculators do not do the middle percentages, but the color ones will. So here's 50% in the middle, and then, so basically this is your C. So even though it's supposed to be symmetric, it's just the way I drew that, that is not symmetric. So, and then what happens is, obviously, D's are lower than C's. 15% are going to get B's, and 15% are going to get D's. Now, let me ask you this. When you consider the C's, D's, and the B's, what percentage of the curve has now been accounted for? 80%. So if 80% of the curve is accounted for, what percentage is not? 20%. And 20%, half of 20 is, so there you go. So that should enable you to figure out everything. All right, so we want to figure out these percentiles. So easy enough. This is the 10th. This is the 25th. This is the 75th. And this is the 90th. So yeah, middle 50%. And this is kind of an easy, not really easier per se, but in large, again, the purpose of grading on a curve is for larger classes. Now on lab 2, that is due next week, a week from today, on that lab, what you'll see is you will see uh, something that's not quite a grading curve. It's going to pertain to hours of playing Grand Theft Auto. Now, we can go into the wonderful calculator here and do some inverse norm action. And it's easy enough to do that on this calculator here. We go to inverse norm, and you enter the area, and we're going to enter the mean and standard deviation. The mean is a 55.9, and the standard deviation is a 10.3. And we'll round these grades to 2 decimal places. So, let's round it to just 1 for these. So 42, okay, come on. So yeah, 42.7 for that. The 25th percentile, so we'll go back to inverse norm, do 0.25. What the? No, I didn't want to do that there. Yeah, 0.25. And let's see here, 48.95 or to the nearest 10th, that would be a solid 49. For the 75th percentile, let's see what that's going to be. So we'll inverse norm 0.75. And now obviously that's going to take us above the mean. And let's see here, we get 62.85, or we could call it 62.9. And then the 90th percentile, we get 69.1. Now, so basically, yeah, this is the spread of your grades here. An F would be below a 42.7. A D would be 42.7 to 49. A C would be 49 to 62.9. A B would be 62.9 to 69.1. And an A would be 69.1 or higher. And yeah, I know there's overlap technically in this, but just for the purposes of calculating this, we're going to go with this. Now, of course, yeah, what would I do in the real world if I were in a situation where I graded on the curve? Probably make the F a 43. Yeah, D would be 43 to 49. C would go up to 63 maybe, or 62, something like that. So now, of course, if you had really felt squirrely, I mean, I don't know why you would, but we can do it this way. If we went and found the middle 50%, watch this. The middle 50%, here's the lovely thing. This calculator does it. And if you notice, it's from 49 to 62.9. We saw that before. Now, just for a larf, from this mark to this mark, we already established that that was 80% of the data, or the middle 80%. If we found the middle 80%, we would have found those same marks just the same way. So yeah, 42.7 to 69.1. It's all the same. So that's how that's all going to come out to work. Now, the next thing I want to do is I'm going to give you one more. This time, I'm going to change the mean ever so slightly to a 57.4, but I'm going to increase the spread to a 12.9. So middle 65% are going to get C's. Now, the next 27% is split between B's and D's. Now, 27%, half of 27 is what? 13.5%. So you just need to figure out the marks, and once you figure that out, we'll be able to do the curve. So let's draw the curve and see if we can't figure this out here. So let's think about this here. So middle 65%, that means, yeah, most of these people are going to get C's. That's the most often given grade at these big state schools. Now, here's the thing. 27% is split evenly between B's and D's. So we established that half of 27 was 13.5. So 13.5% are going to get D's, and 13.5% are going to get B's. Now, that's not the best looking drawing here. Now, so far, 65 and 27 adds up to what? 92. So half of 90, I mean, not half of 92, but 92% of the grade curve is accounted for here. What percentage is not? 8. So half of 8 is 4%. So we have 4% that get F's and 4% that get A's. I don't know if I would go do it like that. Yes? Oh, you mean like A, B, C, D, F? You theoretically could do that, yes. You could theoretically do that, yes, as long as you, but, here's the mean here. So, and I saw a few people saying, the fourth percentile, they would enter like 4 or 0.4. You would enter 0.04 for the area. You got to watch that. Bit of a trap, but that's okay. That's why you're here, to learn it. That's why. So 4 plus 13.5 is 17.5, 0.175. We add 65 to 17.5. So this is the 82.5 percentile, or 0.825. And if we added 13.5 here, this is the 96th, or 0.96. Now, of course, remember, that's, 96% to the left, or 4% to the right. All right, so now we figure out the marks. So if we inverse normed 0.04, 57.4 and 12.9, make sure you enter that properly there. 34.8. Well, the lowest grade I've ever seen a curve in my undergrad years was in physics, where the professor made 16 a passing. But, yeah. 17.5 percentile. Yeah, don't round that. Make it 17.5. And you're at 45.3. And then if we do the 82.5 percentile, We're now at a 69.5. And let's see what the mark is for an A. So an A is the 96th percentile. And that is a, wow, 80. Now, of course, you could have, if you used the color calculator, which, by the way, you are welcome to use during the day here, if we wanted to find the middle 65%, and that's 65% in the center, there's the marks. And 65 and 27 is 92. If I wanted the middle 92%, of course, I only have to basically find two boundaries and do it this way, but they should all look oddly familiar to you. So an F, you know what, let's start with an A. To get an A, you have to make an 80 or higher. A B goes from a 69.5 to an 80. A C is going to go from a 45.3 to a 69.5. A D is going to go from a 34.8 to a 45.3. And an F is below 34.8. So another thing you notice here, the range for that C, that is, let's see, 24 points. The spread for the C's, that's 24 points. That's just about 2 standard deviations. Well, 65% of the grades, yeah, 65%. So, but yeah, if you notice, the distance from, for a B is 10.5 points, and it's the same thing for a D. The distance from end to end on a D is 10.5 points, as it should be. So, the way your unit test is going to work so basically, we're going to start on technically the last part of the unit where we're going to talk about sampling distributions. We'll definitely not finish it today, but basically, aside from 2 of these curve problems, most of your test, that is 2 weeks from today, will basically be one question where I give you a mean and standard deviation, and you'll have to find various probabilities and areas, as well as percentiles. And if you notice, when we had like how many were expected to be made or whatever, we're going to do samples of other than 1. And that's where sampling distribution is going to start. So do me a favor, if you haven't done so, please get on a laptop and go to the course Moodle page. I'll give you a couple of moments to get that moving. Here is what's going to happen. So we're going to talk about sampling distributions. So if you look back in the notes that we've done, for instance, when we did examples like on page 18 and 19, A, B, and C, what we were doing was we were finding these percentages or probabilities based on one subject. And for D, we used that same probability to find the expected number when we had a whole slew of people here. But things are going to change a little bit. And it's not really going to be too bad, I don't think. What's going to happen is we're going to look at the sampling distribution of sample means. So the way this is gonna work, and I'm gonna show you the applet. The applet is on Moodle. There's a link to it on Unit 3. Basically what happens is, think of taking all possible samples of size n from one big population of data, from one big population. What happens is, you would calculate individual means, and basically you would imagine one big population with a population mean of mu and a population standard deviation of sigma, which is what we've been working with. Ultimately, the expected value of the sample mean is simply going to be equal to the population mean, and we're going to see it using this applet in just a few short moments. So just imagine samples, and if we took the mean of all those sample means, it's still going to be equal to or very close to the population mean mu. Now, the standard deviation is going to change. And what happens there is the standard deviation winds up getting divided by the square root of the sample size. Now, our sample size for all of our basic calculations has been 1. So when we divide by the square root of 1, we have the same thing that we started with. But we're going to kind of see how it works a little bit differently here. So long story short, when populations are very large, it is impossible to list all possible sample means. And it literally, the sample mean, the mean of the sample means is literally the same as your population mean, and that is also proven by the central limit theorem. Do we have to do a whole bunch of math proof or whatever? No. So don't freak out about that. But if, let's say, a random variable x has a distribution which may or may not be normal, it'll have a given mean and a standard deviation. What happens is we select simple random samples. And basically, the conclusion is the distribution of sample means will approach a normal distribution. And the standard deviation of all of those is now standard deviation divided by the square root of the sample size. Now, that's kind of a new thing here. That's a central limit theorem. I have been trying to come up with a way to really make this come alive outside of an applet, and for all of my, I've been trying to come up with something that just has never really flown. So here's what I want us to do. So if you go to Moodle and look at Unit 3, you'll see a URL, Sampling Distributions A. I want you to open that, and we're going to use this applet here. So we're going to deal exclusively with means. So here's what will happen. So we can begin this, and this top one is going to be the parent population. And right now, we're going to work with a normal population. We can work with non-normal data, and as you'll see, it's going to be pretty interesting. So what we can do with this is, we're going to do strictly means. So we can do them with a sample size of 5, and let's do a mean with sample sizes of 16. Now, so it's only going to be means here. Now, skew, that skew value mean, basically a skew value of 0 means the data are not skewed in any way. This is perfectly symmetric normal data. But if you notice, the mean is 16 and the standard deviation is 5. So here's what we're going to do. Now, you can animate the choosing of sample means here. Now, that's going to take a while. But another thing you could do, you could do 5 at a time and build that up. Or what you could do is like 10,000 at a time, or even hundreds of thousands at a time. But here's what I'm hopefully going to get through to you. If you notice, whether we took a sample size of 5 or a sample size of 16, did our means change at all? No, the means do not change. This is the mean of all of those sample means. But if you notice, the standard deviations, this standard deviation is 2.24. This standard deviation is 1.25. So, and if you notice, yeah, obviously a larger standard deviation means the data are more spread out. If the standard deviation is smaller, the data get less spread out. And what happens is, when we increase those sample sizes, we are decreasing that standard deviation with it. Now, I chose 5, and I chose 16 for the other one. If we actually did 16 and 25, here's the thing. What's the square root of 16? And the square root of 25 is 5. So if I keep that up, here's the thing. Don't worry about the kurtosis, but what I want you to see here is the standard deviations are more even numbers here because 16 and 25 are obviously perfect squares. What is 5 divided by 4 as a decimal? See? And square root of 25 is 5, so 5 divided by 5 is 1. So if you notice, yeah, this obviously, the smaller the standard deviation, the less spread out the data are going to be. Now, here's something kind of cool. So let's just keep it with 10 and say 25. It doesn't really matter. We can make this a skewed distribution. Or we could even customize it. By custom, I mean like maybe doing this. I don't know. But we can work with a skewed one. So if we want to find the distributions of means here, if we took like hundreds of thousands at a time, the means are still going to be the same thing. But again, it's the standard deviations that get smaller. But that data is obviously skewed here. But what happens is, as the sample size increases, if you can tell, this data where the sample size is 10, it is not as symmetric. And it is a little more symmetric with the 25 here, but not perfectly. So you do have some skew factors in there. Let's see if we can't come up with something really good here. I want to get something that has a good skew factor, a really good one. Yeah, it's kind of like trial and error. I mean, how that skew is calculated, I don't really know. You know what? Here's what I can do. And just do this, get rid of that. No, it's too symmetric. I'm trying to find something that is like really good. Like I really want to skew this as much as I can. I mean, uniform doesn't really do it for us. Oh, okay, good. See, that data is pretty skewed off. And I could do tens of thousands. And the thing that I'm hopefully impressing upon you here is, yeah, the means do not really change. It is the standard deviations that change. But as we get a larger sample size, it's going to be less skewed. So let's see here. Here is something that might be worth doing here. Try it with like a 5. Maybe put something in here that could really skew that. Not there, but not too tall. A little better. But yeah. So if we look here, yeah, when we have a sample size of 5, this data is really screwed up. And that's because the distribution of our parent data is not normal. Now, if the data is normal, which is primarily what we're going to be working with in here, it doesn't matter what the sample size is. That's the other thing that I'm hopefully going to get into your skulls here is, yeah, regardless of the parent distribution, if we have a sufficiently large enough sample size, like sample means of 25, just imagine that you took 100,000 samples of 25 and calculated the means. They're putting them right here. They're doing that with simulation. There's ways that you could, there's ways that that I've tried to come up with that, to use StatCrunch, and for some reason it just never works as well. But if we do a normal distribution where the parent data is normal, and if we took means of size 2 and say 10, and we did like 10,000 of them, see, it doesn't matter. It doesn't matter here because the parent data is normal, and so it doesn't matter. So the mean of means, the means with a sample size of 2 is nicely symmetric. But with 10, it's even more, narrow. So that's how that works. Yeah, I have really tried, again, to come up with some other ways to 1-1 on all this. What was I trying to talk about here? Basically, for a sample size of n that is larger than 30, that's kind of the line here that every statistics book uses. This is basically regardless of any of the parent data. I mean, let's be realistic here. I mean, in the real world, when we're looking at large amounts of data, it is going to be normally distributed. There's just no other ways about it. Now, if the original population is normally distributed, it doesn't matter what size that sample mean is. The sample means will be normally distributed. So this 30, and you probably haven't read many statistics books, and I wouldn't expect you to, but I have almost every statistics book because I'm a nerd like that. I mean, come on, I'm a nerd. That's all there is to it. Every statistics book I have read this side of Canada would say basically 30 was the magic number. So basically any population distribution, and it corresponds to sample means whenever the sample size is greater than 30. This becomes pretty normal. Now, for a normal population distribution, it doesn't matter. But I don't even know why we have a 1, 2, 3, and 4 here. It should really be these here. So what's going to happen is, in normal distribution problems now, we're going to say, we're going to take a sample of so many people. What is the probability that that group's sample is between this or that? That's where things are going to change a bit. Now, you have estimators. You have unbiased estimators, which are sample means, variances, and proportions. Now, we've been dealing with sample means this whole time. Now, in the next unit, we're going to be doing hypothesis testing with the normal distribution and confidence intervals. And here's the thing. We're going to be doing them for means and later proportions. Now, proportions look scary, but it's really not. Variances is something that would be done in Stats 2. And yeah. So those are unbiased. They target the population parameter. And what we see is, yeah, when we take sample means of data, they come very close to the population mean. Now, biased estimators do not target. Now, do you actually have to know this for the test? I'll be honest, no. But medians, ranges, and standard deviations, they're biased. They do not target the population parameter. And we can actually even see that if we did mean and median here. If we actually did median calculations, see, that's normal distribution. If we did a skewed one, see, yeah, the median is kind of off target here. But do we actually have to know that? No. So we sample with replacement. Now, are we actually going to be doing this? No. What's going to happen is basically think of just some large slew of data, like millions upon billions of data entries for something. That's how the normal distribution is going to work. And basically, we're going to be selecting relatively small samples, like samples of maybe size 2, 5, maybe even 20 or 25. But when you think about it, you know, if we sampled with or without replacement, it really makes no difference. Now, simple random samples are the way we do it. Because, you know, voluntary response or convenience samples could easily result in wrong results. And when you think about it, look at every presidential poll. We have an election coming up in a month. And without going in anywhere into it, just, you know, make sure you're paying attention to every poll. Last thing I'll say about polling, let's think about this. Does it matter? You know, you look at national polls. Should you even bother with a national poll for the president? Not really, because the president is elected through the Electoral College. It is with states. It's not a nationwide popular vote. So, that's that, and we'll get into this after we come back from break. All right, good timing. Let's come back to this. So, basically, again, sampling with replacement, with and without replacement, really not going to make any difference here. The purpose of all this, basically, is I throw this condition in here, the central limit theorem, for all samples of the same size n with n is greater than or 30, and that is for any parent data. So if you saw me playing around on StatCrunch here, I'll show you why I had trouble getting this off of the ground. Because, and here's why, if I could open it first. So, I could simulate data with, I choose chi-square because, chi-square is a skewed distribution. And if I were to do like a dot plot of it, you could easily see that, that data is skewed. Now, when it comes to sampling, if I selected that and I did like sample sizes of 10 with like 100 samples, maybe, let's see here, maybe do that, I don't know. Okay, yeah, see, that's where, this is why I can't get this off the ground like I should. But basically, since we're going to be working with a normal distribution, we're going to be working with normally distributed data, the mean is still going to be mu, and this becomes our standard deviation. So, yeah. And why is this like stuttering here? So, yeah, basically when parent data is already normal, n does not matter. So basically, that's all the central limit theorem. So basically, our z-score kind of gets updated, so to speak, by taking the value minus the mean and dividing it by that. Now, the really nice thing is for the calculator, you can do that on the calculator here. Now, if you have data that are normal, uniform, or U-shaped, basically what happens is, regardless, as the sample size gets larger, it doesn't matter what kind of data we're dealing with. The sample means all get normal. So if the data is skewed like this, see, the TI Inspire actually is easier to do with this, but what happens is if we took samples of size 100, that's not perfectly normal, but that is pretty good considering, look at that original data. Whereas if you did samples with size of 20, it's not going to be as nicely normal. But again, we're going to be dealing strictly with normal data. And I swear, I keep saying I'm going to update this to coincide with inflation every year. And when you think about it, cell phone bills, generally, like our cell phone is bundled today with AT&T and whatnot. So cell phone bills for residents of a city have a mean of $63 and a standard deviation of 11. So if we took random samples of 100 cell phone bills and we calculated the means here, what happens is the sampling distribution, the mean is still going to be $63. However, the standard deviation, I chose 100 partly so that, the square root of 100 is going to be 10. And it's going to come out to a nice even value here. And what happens here is if we had sample means, like if I said, what is the probability that this group of 100 cell phone bills is larger than $74, you could probably say the probability is next to nothing based on this. But individual $74, there's a lot. But if it was like $100 bills, yeah, $74. We don't have that. So, finding z-scores, it looks very familiar because it is, and you're going to need, we're going to be doing that again in the next unit anyway. So, again, nothing new. Now, we're going to finally put it all together once and for all. Suppose the gas mileage of four-door compact to mid-size gasoline, that's non-hybrids. I'll tell you, some hybrid vehicles I think are better than others. Think of Camrys, Civics, Accords, Corollas, Sonatas. Yeah, I'm talking foreign companies, but yeah, like does Ford even make a passenger vehicle car anymore? I'll have to look at that. But here's the thing. For A, B, C, and D, and all the way through F, basically, we've all done that before. So, I'll let you do A here. Now, another term you might have seen here, z-scores underneath, standardized basically is just another fancy term for z-scores. So if I draw a normal curve, it's not the best looking one, but we'll deal. 28.3, and that's the miles per gallon. And underneath that, I'll put the z-score. So we will go 1, 2, and 3 above, 1, 2, and 3 below. -3, -2, -1, 1, 2, and 3. So we'll add and subtract 4.7. $28.3 minus 4.7. So you're at 23.6. Then 18.9 and 14.2. And if I went above that mark of 4 points, adding 4.7 miles to the gallon, you have 33, 37.7, and 42.4. Yeah, like 40 miles a gallon, like for one of those old cars. Or if you, I think it's in lab number 1 with the Dodge Omni. Dodge Omni, that was a great little car. All right, so if you notice for B, I want you to determine the actual z-scores. And on your test, you'll have a problem where I'll say determine the actual z-scores, and I didn't say write it in a complete sentence, but we'll do this one with a complete sentence as well. So 25 is going to be below the mean, 30 will be above the mean. So I always like to draw a picture. You have 28.3 in the middle. You have 25 to 30. You don't have to be perfect or anything like that. 25, that's going to be 25 minus 28.3 0.3 over 4.7. And that'll be negative 0.702. I said 2 decimal places, but I'm going to do it to 3 because why not? And then for 30, we're above the mean on that, although not much. So yeah, 30, and we get 0.362. So we just normal CDF these two values, negative 0.702 to 0.362. And wow, 40% on the nose. 40% of sedans get between 25 and 30 miles per gallon. All right, probability that a randomly chosen sedan gets over 32. Now, you can do that straight up in the calculator. Go above 32 miles per gallon. Now, keep in mind, I always draw the curve. 28.3, and here's 32. And I want the area to the right of that. So how I would use the calculator for that is easy. I would normal CDF. My lower would be 32. Now my upper, since I don't have an upper, I could use some big number, 1,000. That's fantasy land, but we'll pretend it exists. 1,000 miles a gallon, maybe a moped. Nah, not even that. And the standard deviation is 4.7. Thing is, yeah, this calculator does not have an infinity feature. Now, of course, you can also use StatCrunch to figure things out. And yeah, you can go like greater or less than. But if you notice, it's going to be 0.2156 or 21.56%. So that's how that's going to work. So again, make sure you know like what z-scores you're entering and whatnot. Now, below 25 or more than 30, I always love to throw one of these on your test. And here's why. So here's the thing. We have 28.7, and we would go below 25 or above 30. Here's the thing. Below 25 is here. Above 30 is here. Now, you can find two individual probabilities. And if you know that there's a quicker way, don't tell us yet, because I'm going to. But if I wanted to find this, I would go to normal CDF. And here's the thing. I don't have a lower, so I'll just use a big negative number. Probably could have gotten away with 0. And then 25. And that would be 0.2413. Now, if we want to go above 30 miles per gallon, the lower is going to be 30 and the upper is going to be a big number. I mean, theoretically, you probably could even stop at 100, but you know what? Why not? Why not just do this? And we get 0.3588. And you add the two together. And you get 0.6001. Now, here's another way you could have done this. What is this area that we've already figured out? Between 25 and 30 miles per gallon? We have between 25 and 30 miles to the gallon here. You answered that question earlier. I think you answered that on question B. What was it? 40%. Now, technically it should have been 40 or 39.99, but 40%. The whole area under the curve is 100%. 100 minus 40, 60% that way. Now again, why is this off by 100th of a percent? Well, because we rounded the z-scores off, accordingly, and got something slightly different. You could have said 60% or 60.01%. It all works the same way. But basically, remember complement rules for probability. It's 1 minus what you do not want. That's all. Now we're going to go below 20 miles a gallon. It's going to be pretty small. All right, so let's go below 20. I don't think it's going to be very much. One way to improve your gas mileage, don't drive fast. I know that sounds so simplified, but it really is. Like when I drive my car, and I'm driving like 65, my gas mileage is at its best. Whereas if I were driving 85, yeah, it's not. But when am I driving 85? Maybe in Texas. All right, so yeah, like negative some big number to 20. Oh, not 2, but 20. 2 miles a gallon. 0.0387 or 3.87% of the sedans that are going to get below 20 miles a gallon. That's about right. Now, 1 billion sedans are out on the road. There's probably more SUVs today. How many of them would you expect them to have gas mileage greater than 45 miles a gallon? So you're going to have to find this probability of 45 miles per gallon. All right, so yeah, 45 miles a gallon, and that's probably too far, 28.7. So we want to figure this out here. 28.7, no. 45 is your lower. See, I got to think for a second. And then for the upper, since I have no upper, I'll just use a big one. And I get 1.9 times 10 to the negative 4. Now, here's the thing. On day one, scientific notation. Now, if you gave me 1.9 as the answer, that's not right. Now, that negative 4 basically means we move the decimal place 4 units to the left. So we go 1, 2, 3, 4, which is 0.00019. Now, N times P, that's basically 1 billion times 0.00019 times that's a million, and that's a billion. 190,000 of those would have gas mileages of 45 or higher. And gas mileage is also a function of how you drive. And as much, I think cars are spying on us in a way. I mean, do I sound like some kind of conspiracy theorist? But they do have black boxes in them that literally can tell you, like if you're ever in an accident, it can actually say like what the speed was when you hit the brake or didn't. And so all this talk like, oh, electric cars, they can take over. You know what? They can do the same with gas. They haven't. All right, now, this is where it's going to be different here. So, suppose that 8 sedans are chosen at random. Now, what is so this is different from the part we just did here, because the previous part that we did, part F, said how many would be expected to do this. What's happening here is the mean gas mileage of this sample of 8 sedans exceeds 32 miles per gallon. So think of like 8 sedans that are chosen. Now, 8 times 32 is 256. Now, so basically, think of it like this, although you really wouldn't need to. Like there are 8 cars, and their total gas mileage is 256. So, I don't know, what if 7 of you had cars that were getting 0 miles per gallon and mine was getting 256? Well, doesn't matter which way it's happening, it just matters that mean is 32 across all 8. So here's the thing. 32 miles a gallon. Now, the mean is still 28.7. And if you notice, we did, for part C, we did 1 sedan getting over 32. Now, in this case, 32, the z-score, this is 8 sedans. So basically, it's going to be 32 minus 28.7. Now, what's the standard deviation again? 4.7. See, this is unfortunately the only one you can't really do straight up on the calculator. 4.7 is going to be divided by the square root of 8. Now, how can you set this up in your calculator? It's actually very easy. 32 minus 28.7, you could just do divided by 4.7 over the square root of 8. You could do it that way, and we get a z-score of 1.986. So for problems like this, you're going to have to be able to find the z-score. There's just no way around it. Or if you really want to get fancy, you set up the fraction. 32 minus 28.7, and inside of here, you can do another fraction. 4.7 over the square root of 8. Here's the thing, it's the same thing. Now, this z-score is 1.986. So you would normal CDF, we're using the normal curve here, 1.986 to 10, with a mean of 0 and a standard deviation of 1. In other words, I am talking back to standard normal. It's strictly standard normal for this. So I am going to go back to normal CDF, 1.986 to, oh yes.
How do you know when to do the square root and not?
Okay, how do you know when to do the square root? See how it says, what is the probability that the mean of the sample of 8? That's when n is going to be 8. The previous ones didn't have well, technically, you divide by the square root of 1, which is just 1. So technically, the sample size has always been 1 until now. So we're back to standard normal here. And we get 0.0235. Or 2.35% of size 8 samples. I didn't ask for a complete sentence, but I will. Have a mean gas mileage, have a sample mean above 32. So now I'm going to give you 20 sedans. Well, let's fix this last one. So here we go. Now, if you made this mistake, I would probably dock you very little, because the work would be right. Yeah, so 2.227. So we're going to just, wow. Boy, am I a bonehead today. .013. Or literally 1.3%. So yeah, that changes things a little. All right, so we're going to go below 26. So here is 28.3. Wow, I can't believe I made that mistake, but that's okay. So the z-score, now let's keep this in mind here. Z-score is going to be a negative value. It'll be 26 minus 28.3. Let me redraw that just a little better. 26 minus 28.3. The standard deviation was 4.7, but this time this 4.7 is divided by the square root of 20. So 26 minus 28.3 divided by 4.7 over the square root of 20, and we get negative 2.188. And what happens here is, yeah, the z-score is negative 2.188. So we normal CDF that, this time from negative 10 to negative 2.188. And we get 0.0143. Or 1.43%. Now, if it were one vehicle, yeah, it would be, the probability would be a lot higher, but since it's 20, it's like everyone in here having a car. Yes.
How do you know when to put 0 and 1 for the mean deviation and action?
Okay, so why did I put 0 and 1 for the mean and standard deviation? Because for the normal distribution, standard normal distribution, that's when the mean is 0 and the standard deviation is 1. That's when we found z-scores. In other words, and I'm probably going to be saying this again and again, you probably should write this down. When you're dealing with central limit theorem problems such as G and H, you have to find the z-scores. End of story. There is no way around it. You have to find the z-scores. Now, for I, we learned how to do that idea in an earlier class. The top 5% of gas mileages of sedans. So what we're going to do here is we are going to find the raw z-score and convert it to the proper value by hand. We'll only have to do it once. The standard normal distribution again, but we will not use normal CDF for I. To find that top 5% mark, which calculator function will you have to use? Inverse norm. Excellent. So, in the words of Gary Gilmore, let's do it. Now, chances are, and if you don't, that's okay, but if you're a geek like me, you'll probably remember this. You know, top 5%, that means 95% is to the left of that. So I can find that z-score. So basically, what am I doing here? I am basically just verifying your math skills. 95% to the left, and it's 1.645. But if I did 5% to the right, it's the same thing. And yeah, see, the same thing. So now z is x minus mu over sigma. See, here's the thing. N is going to be 1 for any of these problems. So basically, you have 1.645 equal to x minus 28.3 divided by 4.7. So we multiply both sides by the 4.7 as we learned last time. And 4.7 times 1.645, and we'll round that to 2 decimal places. 7.73 equals x minus 28.3, and we add 28.3 to that. So 7.73 plus 28.3. X is going to be 36.03 miles per gallon, or now, since I asked for top 5%, would it be higher or lower? It's going to be higher. Now, if I asked for a complete sentence, you would simply say the top 5% of gas mileages for sedans is 36.03 or higher. All there is to it. So yeah, bottom 1%, or cars that suck. Well, here's the thing. It could also be your driving habits. If you drive on highways like going 60, 55, 60, straight highways, you're going to get good gas mileage. Like when I drive to Pittsburgh, for instance, I have to go up and down several mountain ranges. Although it's very beautiful going through West Virginia. Everyone makes jokes about West Virginia. They're really uncalled for. Not 10. I don't know what I was thinking. Yeah, 1%. So basically, you could just inverse norm 0.01, not 1, 28.3 for the mean, and 4.7 for the standard deviation. So if we inverse norm 0.01, and again, we're changing the mean and standard deviation, and that's obviously to the left, 17.37 miles per gallon, or lower. Now, before we leave, so anytime you're asked for a percentage or a percentile, you immediately think inverse norm. Now, before we go, what if I decided to normal CDF from that big value to 17.37 with a mean of 28.3 and a standard deviation of 4.7, not 4 negative 7, but 4.7, I get 1%. Normal CDF is what you use to find areas. Inverse norm is what you use when you're given the areas. So what's going to happen is your lab is due Wednesday. Case study is out. Make sure you're getting ahead. And that's it. All right, so the top 0.5% of gas mileages. So we want to go ahead and figure that out. So top 0.5%. So to do that, we draw the normal curve, and it's not perfectly scaled here, but as I said, we want the top 0.5%. And basically 0.5%, you have 99.5% to the left. So that's what you're going to get for that. So we can just use the inverse norm feature to figure that out. And to do that, the inverse norm will be 0.995 with the with the mean being 28.3 and the standard deviation being 4.7 miles per gallon. So we figured that out, and it's going to be, 40.41. So basically, the top 0.5%, that's half of 1%, it's going to be 40.41 miles per gallon or higher. Now, believe it or not, you can actually do this one on StatCrunch. Now, 0.5%, I want to point out to you, 0.5% as a decimal would be 0.005. So if we go into StatCrunch and we go to Stats, Calculators, and we choose Normal, and going back to this, the mean was 28.3 and 4.7 And since we want this to be greater than a certain mark, 0.005, it's going to give us the value that we want of 40.41 miles per gallon. Now, the other thing you can do, believe it or not, is if you go to options and copy and copy image, this is one thing that you can do for your case study. So what I'm trying to do is I'm trying to put that in here, and I think I finally succeeded. So yeah, 40.41 miles per gallon or higher. And yeah, you'll see 40.41 down in here. All right, so what I want you to do is, finish this, do the middle 50%, and then you'll do the IQR. IQR is actually going to be real easy to do, and we're going to change that last one to top 1%. All right, so yeah, middle. So let's see, middle 50%. Oh, I don't know why this thing is like kind of stubborn on me here. And not the best looking bell curve, but we'll deal. So, even though this is a terrible, horrible drawing, I'm still going to go with it here. Now, if we have 50% in the middle, that means there's 25% on each end. And it's true. You can use the 84 outright. If you have the color one, it does center. But if you only have access, especially at home, to a black and white, number one, you could use StatCrunch to do your assignment to figure it out and draw it. Yeah, there's no rule against that. But I'm going to still, I'm hanging on to the old school here where we didn't have the luxury of having the center. And believe it or not, Casio actually came up with that first. Casio beat Texas Instruments to the punch. So if I want the 25th percentile, this gas mileage is not right. Oh, it should have been 0.25. Wow. I made a big mistake here. So yeah, 25.13. And then if I want the 75th percentile, and that's because 75% lies to the left of it, it's going to be 31.47. Now, on your unit test, you're going to have access to a color calculator because I have a whole class set of those. So, yeah, it's very true. You could have just done it in one shot, done inverse norm of the middle 50% in the center. And you see that you have the boundaries. Now, let's say you're at home and you're working on your lab assignment or something, and you only have a black and white calculator and you want the middle 50%. Well, believe it or not, you can do it on StatCrunch. Watch this. Now, I'm going to do this, where I'll have to open it in a separate, smaller window. Still trying to get used to this computer. Mainly Windows 11. All right, so if I go between here and I type in 0.50, middle 50%, which is what I really want, it computes it and I get the boundaries. Now, and if I want to copy and paste, I'll copy that image right to here, and oh, beautiful. And here's the thing. Yeah, it gives me all these decimals, but if you notice, yeah, it gives me the boundaries. Basically, it's going to be 25.13 to 31.47 miles per gallon. That's the middle 50%. And I am going to ask you middle 50%. And in addition, I am going to ask you for a middle like 70, 60, 70, 80, or 90% on the test. Now, the IQR, now, you're probably thinking, how the hell do I do an IQR for this? Well, believe it or not, it's actually a lot simpler than you think. Because, okay, think back to IQR. When we were working with box and whisker plots way back in that first unit, what did you do to calculate the IQR of a set of data? How did you do that? What did you have to do to calculate your IQR? Nope. The third quartile minus the first quartile. Now, the third quartile also represented what percentile? 75th percentile. And the first quartile represented what? The 75th and the 25th. Well, hey, we have those values right here. The 75th percentile was 31.47 and minus 25.13. Hence, the IQR is going to be 6.34. Now, I want you to figure out the top 1% of gas mileage. Now, remember, that lab is due today. What is the top 1%? Well, if we want the top 1%, that means 99% is below that mark. So it's just a simple inverse norming of, you could do 0.01 to the right or 0.99 to the left. Either way, it works. And we get 39.23 or higher. So that is officially going to conclude the new material for this unit. So what I'm going to do now is we're going to go kind of part A, where we're going to go 3 standard deviations above and below the mean. Below here. So the mean is going to be 50. So if we call X the number of texts, and underneath that, you're going to put the z-score. So we will go 1, 2, and 3 below, 1, 2, and 3 above. And yes, this is not the best looking curve, but eh. So let's see here, 12.4. So yeah, 50 minus 12.4, that's 37.6. Minus 12.4 again, 25.2, and 12.8. And of course, if we go above, we can add increments of 12.4, and we see a 62.4, 74.8, and then 87.2. So that's what we get for this. All right, so that's basically going to be your part A on the test. So let's see here. Part B, I don't know. In fact, one thing I'm going to do here is, for my sake, I'm going to label the mean and standard deviation again, because, probably. Okay, so let's see here. So for this one, what is the percentage of people who send between 40 and 65 texts per day? Find the z-scores. So this is one where you'll have to do basically the whole Monty and write as a complete sentence. You're not going to have to write a complete sentence on your test. One, let's see here. So we're going to go between 40 and 65. Now keep in mind the mean is 50. So we're going to have 40 and we're going to have 65. So we've got two z-scores that we must calculate. Z-score corresponding to 40 is 40 minus 50 over 12.4. And the z-score corresponding to 65 is 65 minus 50 over 12.4. So when we do this, 40 minus 50 over 12.4, we get negative 0.806 or negative 0.807. If you gave me 0.806, I would accept that too, but that 5 makes that a 5, and then that 6 becomes a 7. So, and then 65 minus 50, and that's above the mean, so that means it's going to be a positive z-score, 1.209, or we could just call it 1.21. And those are the two z-scores that we have. So we can inverse norm those two. Now, here's not inverse norm, I'm sorry, normal CDF. Because here's the thing. Since we're dealing strictly with z-scores are the standard normal. And since we're dealing with the standard normal, the mean and standard deviation are still 0 and 1. And we get 0.6770 or 67.7% of people send between 40 and 65 texts per day. So that's what we get for that. And so each part will be worth a certain point total. obviously this part would be worth more than others. Like we're going to do 3 or 4 more where we're going to find percentages or probabilities or what have you. But this will be worth more because you've had to do basically everything for this. For the next ones, we really, don't have to do a complete sentence or anything like this. So what I mean by that is, for instance, in part C, what is the probability that a randomly selected person sends 35 or fewer texts in a day? So let's draw that. So here's 50, here's 35, and here's our little drawing. So what I'm going to do is, instead of having to find the z-score, because, well, I said you don't have to. But here's the thing. We have no lower bound, so we're going to use a large negative number. And then the upper bound will be 35, but we can't use 0 and 1. We have to use the prescribed mean and standard deviation of 50 and 12.4. And if we see that, didn't want to hit that, but we've got 0.1132 or 11.32%. All right, now, pretty small. So I always like to draw the curve with with the mean. And so here's the thing. When I normal CDF this, if I want to do it outright, 90 represents now my lower value. 90 represents your lower value, and the upper can go on and on forever. So we'll just use that. And we get, scientific notation. 6.28 times 10 to the negative 4. Now, what this means here is you move the decimal place to the left. How many places? 4 places. So you go 1, 2, 3, 4. And it's going to be 0.0006. Or if you want to give me more, 0.000628. But I would gladly have accepted that one. Now, I probably wouldn't ask you this on a test, but I'm going to ask you this. Percentage of people sending 120 texts or more. All right, so we're going to go 120 texts or more here, and I reckon, this is going to be pretty small. So we go back to our wonderful little normal CDF, and this time, 120. That's like several standard deviations above the mean, and it's 8.27 times 10 to the negative 9. Now, I want to emphasize something. The probability is not 8.27. It is not that. You have to know what to do with that decimal. Now, here's the thing. 10 to the negative 9, 827. If you gave me that, that would be okay. But to 4 decimal places, what is this really? 0. 4 decimals. And I'm going to throw this one at you now. What was the original one? And I'll just move this one down a bit, but so let's do it the quick way. Because here's the thing. 40 and 65, didn't we already figure out the probability between that? Yes. Well, what was it?
Yeah.
67.68? Okay, you can use that. I like that. Or 67.7. If you're off by 2,000s, oh my God, we're going to, yeah, no. So 67.7% or 0.677. But if you use 0.6768, your answers can vary a little. I'm very open to wiggle room, but if your answer's like, if you gave me like 0.664, yeah, then we're having a problem here. So 1 minus 0.677 is 0.323 or 32.3%. So I reckon I'm going to ask you 2 of these type of questions. I'm going to ask you one where you've already figured out the answer and one where you didn't. So for part G, here's the thing. It's actually going to be a lot easier than you think here. So here's 50, here's 45, and I want this, and then I want this. So there's literally 2 ways to do this. One way to do this would be to find these individual sides, and basically we go back to normal CDFing from negative a bajillion or whatever to 45. Keeping the mean and standard deviation the same, we get 0.3434. And if we want to go above 70, we go from 70 to a big and get 0.0534. Add them together and we get it. 0.3434 plus 0.05. 0.0534, and that's 0.3968 or 39.68%. Or there's always an or. In fact, I knew somebody with the name Or when I was in school. He was a grad student, not from this country. Nice guy, didn't understand a word he said, which was most of my graduate TAs. 0.6032 is what we do not want. 1 minus 0.6032, which is 39.3968. So you kids have two ways to figure that out. So guess what? It's break time. Let's see what we've got here. Group of 8 people. And we're going to go higher than 60. Keep in mind the mean is 50. So the z-score is going to be 60 minus 50 over 12.4, but that 12.4 in turn is now divided by what? Square root of 8. Don't try to, don't figure out the square root of 8 in advance and then divide that into 12.4. Do it like this, please. It's going to make your life a lot easier. So we have 60 minus 50. We set up a fraction. And in the denominator, we set up another fraction, 12.4 over the square root of 8. And we get 2.281. So we would normal CDF, you don't have to write this, but because we found the z-score, we have to go back to standard normal. 2.281 to large, you could use 10. 50 and 12.4. Oh, I broke my own rule. What was I smoking? Oh, nothing. I never smoke. All right, so we go back to normal CDF, 2.281 to a large number. We could just get away with 10, and 0 and 1. And it's going to be 0.0113 or 1.13%, or basically a group of 8 has a sample mean text rate above 60 per day is 0.0113 or 1.13%. All right, now and I would probably phrase this a little bit nicer. Ah, 45 texts per day. texts per day or fewer. And what was that? That was part H, so this is part I. Next part will be J. So here's 50, here's 45. So the z-score is going to be 45 minus 50 over 12.4 divided by the square root of 14. So we know the z-score is going to be negative here. And negative 1.509. So we basically just want to normal CDF that from negative 10 to negative 1.509. And let's see what we get here. .0656 or 0.0657 or 6.57%. All right, so there's that. Now we're going to get into percentiles and stuff. So how do we do this one? Well, and I know we would only send text messages in whole numbers. So what I'm going to do though is, I'm going to round this to 2 decimal places, even though we can't send part of a text. But what is the top 15% of text messages? And this is where you will have to find the raw z-score and solve it for the number of texts. So in other words, you're not to 2 decimals and complete sentence. So this part would be worth more. So top 15%, and I know again the number of texts, but we're going to round this to 2 decimal places. So here is 15%, the top 15%. Now that means there's 85% below it. Needless to say, though, we need a z-score. And so if we go into inverse norm, 85% to the right, or 85 to the left, 15 to the right, I get 1.036. So now remember this formula, z is x minus the mu over sigma. So 1.036 will equal x minus 50 over 12.4, and then you would solve this for x. You only have to do this one time where you actually have to find the raw z-score and solve. After that, you can just do it all straight up in the calculator. So we multiply out both sides by 12.4. And we get 12.85 equal to x minus 50. Well, we add 50. 62.85 will equal x. So the top 15% of texters send 62.85 or more texts per day. How did I find the z-score? I inverse norm. And since I asked for the raw z-score, top 15%, and that area is 0.15, and it's to the right. And I get that z-score of 1.036. And then I get this equation of, oh, I need trouble seeing here. Yeah, 1.036, or I could just make this bigger. Can I just do that? So I plug it all into that z equation in blue, and then I solve it. Now, for the next few parts that I'm going to ask you, you can do these straight up in the calculator. In other words, you can change the mean and standard deviation appropriately. So for K, let's do top 5%. L, top 2%. And again, you can do these all straight up. So yeah, top 5%. And yeah, I'm drawing this curve, and that's probably more than 5% here. So what I mean that I can do that outright is the area is going to be 0.05, but I'm going to change my mean and standard deviation to 50 and 2.4. And 5% to the right, and it's going to be 53.95, or what? Top 5%. Top 53.95 or higher. All right, let's take a closer look. I had the wrong standard deviation. Wow. Chalk that up to being a bonehead. Nah, I'm not a bonehead for that, but wow, that was not good. 70.4. Yeah, that should be. There we go, yeah. Oops. Yeah, I should have kind of caught that because, yeah, my standard deviation is relatively large. Now, in a more advanced version, you know, what I could have said is, yeah, top 5% is this mark. If the top 5% is this mark and the mean is this, what is the standard deviation? Ooh, that could have been fun to solve, but we're not going to do that. Top 2%. Well, we could do, you know, not 0.2, but 0.02 to the right, or 0.98 to the left. So the mean is, again, 50. Standard deviation is 12.4. And 75.47 or higher. Now the top 0.1%, ooh, that's a good one. 0.1% on this side means what percentage on the bottom? 99.9%, or basically 0.999. So basically, you can do, 1/10 of a percentage is 0.001, and that's 88.32 or higher. Or you could have done, if you would inverse norm 0.999, but to the left, you would get the same thing, as you can see right there. Now, the bottom 3%. Let's see what the bottom 3% is. So that's definitely going to be below the mean. So we would inverse norm 0.03 to the left, because that's what we want, and 26.68, or what? Lower. Middle 80%. Now, it's true on the on test day, you'll have a calculator, one of these calculators in front of you. So you could just do 80% in the center, but remember, there's 10% on either end. Inverse norm 0.80 or 0.8 in the center. And that would be 34.11 to 65.89. Now, middle 50%. Well, guess what? We do that again. And we get 41.64 to 58.36. And now the IQR, well, we have the two values that we need. The IQR, it's going to be 58.36 minus 41.64. 0.64, and that's going to be 16.72 for the IQR in town. How many of them would be expected to send 70 or more texts per day? So 70 or more. Did we actually answer that by chance? If we didn't, that's okay. No, we didn't. So don't worry, I'll put J back up here. So here's the thing. We've got to figure out the probability. So we are back to normal CDF. Now remember, the expected number is n times p, which, as I've said before, looks strikingly similar to binomial. Well, that's because in large quantities, the binomial approximates to normal. So we need to figure out what is the probability for having 70 texts or more. And then 50, 12.4, and that's going to be 0.0534. So basically, you have 250,000 times 0.0534. And that's going to be 13,350. This one, and this is an expected count. We're not asking for the sample mean of 250,000 to be 70 or more. We're asking for basically an expected count. All right, so we're going to draw this curve. So we'll start here. These are your level 7s, 0.25%. So the percentile would be the 99.75. So on the area, you would enter 0.9975. And then the next 2.75% down are level 6s. So 2.75%. So what percentile does this put us here? So 0.25% to the right, and then we have another 2.75%. So 2.75 plus 0.25% is 3%. So there's 3% to the right. What percentage is to the left? 97. And then level 5 players are represented by the next 6% down. So what would the percentile be for this one? 91. And level 4 is represented down by the next 17%. So basically 91 minus 17 is what? 74. Now if you added, 26%, this is 26% above it. 74% below it. And then the level 3 players are represented by the next 39% down. So if I did, 74 minus 39, that's going to put me at 35th percentile. Level 2 players are represented by the next 24%. So this would be the 11th. And level 1 players are represented by the rest, which is 11%. Now you just have to inverse norm 1, 2, 3, 4, 5, 6 different cutoffs. Now keep in mind the mean is 43.12 and the standard deviation is 9.78. Did I write that? Yeah, 9.78. And 9.78, and we're going to go from the left. Of course, we could have started from the other side if we wanted. So this is 31.13 hours. If we figure out the 35th percentile, $39.35 hours. Now the 74th percentile, we're going above the mean. $49.41. The 91st percentile, basically all you have to do is figure out these percentiles. 56.23. The 97th percentile, 61.51, and then the 99.75 percentile, or top quarter of a percent, is 70.57. So yeah, level 7 is your extreme gamer. 70 hours in a month you're playing. I don't know. Well, in the summer maybe, but during the rest of the semester, definitely no.